Have you ever wondered what secrets lie just beyond the reach of our senses? What if the universe, vast and infinite, is brimming with mysteries waiting to be uncovered, enigmas that challenge our understanding of existence itself? How did it all begin? And what lies beyond the shimmering stars scattered across the cosmic ocean? Join us as we embark on a journey to unveil some of the most perplexing wonders of the universe, from the fiery birth of stars to the tantalizing search for alien life. About 13.8 billion years ago, the universe as we know it sprang into existence with an event known as the Big Bang. This wasn't a typical explosion, no fiery blast scattering debris, but a breathtakingly rapid expansion from a single point of unimaginable density and searing heat. In the fleeting fractions of a second that followed, the universe ballooned exponentially, cooling as it stretched, creating the conditions for the fundamental building blocks of matter to emerge. Tiny particles like quarks and gluons surfaced, eventually joining forces to form protons and neutrons, the essential cores of atoms that compose everything we see, touch, and even ourselves. As hundreds of thousands of years passed, the universe cooled enough for protons and electrons to merge into neutral hydrogen atoms in a serene era known as the recombination epoch. This calm period allowed the cosmic microwave background radiation, the ancient echo of the Big Bang, to travel freely through space, a relic we can still detect today with sensitive instruments, painting a picture of the universe's earliest moments. Over billions of years, gravity became the master sculptor, gathering matter into stars, galaxies, and the intricate cosmic web that forms the structure of the universe. Though scientists have crafted sophisticated models to explain these phenomena, the very first moments after the Big Bang remain a captivating mystery, fueling relentless curiosity and discovery in the field of cosmology. Speaking of exploration, have you ever dreamed of commanding your own starship and venturing into the far reaches of the galaxy? Enter Star Trek Fleet Command, an epic 4X MMO game that plunges you deep into the expansive Star Trek universe. As a commander, you manage your treasury, complete daily missions, and battle foes to earn points and unlock valuable rewards. Recruit legendary characters spanning over 50 years of Star Trek lore, pilot iconic starships like the USS Enterprise, engage in intense battles, forge alliances, and expand your territory. And there's more. The latest update introduces the Mirror Universe, where you can enlist formidable officers like Mirror Picard, a master tactician, and Mirrorborg Data, a symbol of technological might. Don't miss the 7-day login rewards. Log in daily to claim gifts, and after 7 days, unlock the epic Romulan officer Nero. I've been playing, and I can say it's a strategic, captivating experience. The thrill of cosmic exploration, stunning visuals, and constant updates make it a must-play. And it's free on desktop and mobile, letting you switch seamlessly between devices. Just scan the QR code or click the link to download Star Trek Fleet Command and start your adventure. Use promo code BOOST to claim a beginner station upgrade pack with 300 Latinum, 100K Pastel, and 10K Tritanium. Join millions worldwide, form alliances, conquer territories, and boldly go where no commander has gone before. To measure the age of the universe, scientists employ meticulous techniques. One of the most revealing involves studying the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang that fills every corner of space. By analyzing subtle temperature fluctuations and density variations in the CMB, researchers estimate how long it has been since the universe began cooling after its initial rapid expansion. This method points to an age of about 13.8 billion years. Another crucial approach examines distant cosmic phenomena, especially type Poinet supernova, stellar explosions with a consistent intrinsic brightness. These standard candles allow astronomers to measure distances across the universe. By combining these distances with the Hubble constant, the rate at which the universe is expanding, they calculate how long it took the cosmos to reach its current vastness. This method corroborates the CMB findings, giving us confidence in the universe's approximate age. Additional techniques, such as studying the oldest star clusters and galaxy dynamics, enrich this multifaceted understanding. Yet, even with these insights, the Big Bang Theory leaves many mysteries unsolved. Among the greatest is the nature of dark matter and dark energy, enigmatic substances believed to compose about 95% of the universe's total mass and energy, but remain invisible to direct detection. We infer dark matter's presence from its gravitational influence on galaxies and clusters, but what it truly is remains one of the deepest cosmic puzzles. As we continue exploring, each discovery brings us closer to understanding the grand story of the universe. A story that began billions of years ago, stretches across unfathomable distances, and invites us to look beyond the stars in search of answers. But its exact composition remains shrouded in mystery. Dark energy, the elusive force believed to drive the accelerated expansion of the universe, is even more enigmatic. Understanding these shadowy components is crucial for piecing together the full story of the universe's birth and evolution. Another perplexing puzzle lingers: what existed before the Big Bang? The traditional Big Bang model paints a vivid picture of the universe's evolution from an unimaginably dense and hot state, yet it offers no clues about what came before this cosmic dawn. Several bold hypotheses attempt to fill this void. One suggests a cyclic universe, endlessly expanding and contracting in a grand cosmic heartbeat. Another envisions a multiverse, where our universe is just one of countless others, each with its own laws of physics and realities. These tantalizing ideas remain speculative, hovering beyond the reach of current observational tools. Moreover, scientists wrestle with one of the deepest conflicts in physics: reconciling general relativity, which governs the vast cosmos, with quantum mechanics, the law of the subatomic realm. Bridging these two pillars could unlock secrets about the universe's earliest moments and illuminate the darkest mysteries of the Big Bang itself. Despite monumental strides in cosmology, profound unknowns persist. One of the most glaring gaps is the nature of dark matter. Although it makes up roughly 27% of the universe's mass energy and is vital for the formation of galaxies and clusters, it has never been directly detected. Its properties and place within the standard model of particle physics remain elusive, with scientists only able to infer its existence through its gravitational effects on visible matter and cosmic radiation. Equally baffling is dark energy, accounting for nearly 68% of the universe's mass energy content. Discovered through observations showing the universe's expansion is accelerating, dark energy remains one of modern cosmology's biggest enigmas. Often described as a property of space itself, perhaps linked to Einstein's cosmological constant, this interpretation remains theoretical. Understanding dark energy is key to predicting the universe's future. Will it expand forever, collapse in on itself, or settle into a stable state? Adding to the cosmic conundrum is the Hubble tension, discrepancies in measurements of the universe's expansion rate. This anomaly hints at unknown forces or physics beyond our current grasp, shaking the foundations of established cosmological models. Together, these mysteries reveal not only the vast depths of what we have yet to understand about the universe's structure, but also the thrilling possibility of transformative discoveries waiting on the horizon of modern science. Scientists employ an extraordinary arsenal of sophisticated techniques and cutting-edge instruments to unravel the profound mysteries of the cosmos. Central to this endeavor are telescopes that peer across the entire electromagnetic spectrum, from the longest radio waves to the highest energy gamma rays. These remarkable tools allow humanity to gaze deep into the universe, capturing glimpses of phenomena far beyond our reach. And among these, space-based observatories, such as the iconic Hubble Space Telescope and the revolutionary James Webb Space Telescope, stand out. Suspended in the vacuum of space, free from Earth's atmospheric distortions, they deliver breathtaking, unprecedented views into the heart of distant galaxies, star-forming nurseries, and even worlds orbiting other stars, potential exoplanets that may one day redefine our understanding of life's place in the universe. But the quest for cosmic knowledge does not stop there. Ground-based giants like the Very Large Array and the Atacama Large Millimeter Submillimeter Array, situated in remote, high-altitude deserts, offer stunningly high-resolution images and spectra. These observations reveal the intricate compositions, movements, and fundamental properties of celestial bodies, enabling scientists to test bold theories, refine complex models, and unlock insights into cosmic phenomena such as black hole formation, galaxy evolution, and the mysterious rapid expansion known as cosmic inflation. Moreover, beyond the realm of telescopes, particle accelerators like the Large Hadron Collider, LHC, recreate the universe's earliest moments. By smashing particles together at velocities approaching the speed of light, these colossal machines allow researchers to probe the fundamental forces and particles that constitute the very fabric of reality. This pioneering research sheds light on the elusive nature of dark matter and dark energy, enigmatic components that dominate the universe but remain hidden from direct observation. In addition, gravitational wave detectors such as LIGO and Virgo have opened an entirely new window on the cosmos. By capturing ripples in spacetime caused by cataclysmic events like black hole mergers and neutron star collisions, they provide a novel means of exploring the universe's most violent and enigmatic phenomena. Furthermore, the power of computational science fuels this cosmic exploration. Supercomputers simulate the complex dynamics of galaxy clusters and the evolution of vast cosmic structures, bridging theory and observation. These simulations are essential for interpreting data, testing hypotheses, and predicting phenomena yet to be discovered. By integrating diverse streams of data and employing multifaceted approaches, scientists continuously refine our cosmic understanding, pushing ever closer to answers for the universe's most profound mysteries. Galaxies, those magnificent cosmic cities of stars, gas, dust, and dark matter, remain at the heart of this quest. Among their many enigmas, supermassive black holes lurk at their centers, influencing galactic dynamics on a staggering scale. These colossal black holes, millions to billions of times the mass of our Sun, shape the fate and evolution of their host galaxies. Yet how they formed remains a tantalizing puzzle. Did galaxies assemble around pre-existing black holes, or did these gravitational giants grow by devouring matter within their galaxies? Another enduring mystery is the nature and distribution of dark matter within galaxies. Though invisible to telescopes, dark matter reveals itself through its gravitational grip, forming halos that hold galaxies together and govern their rotation. Scientists continue the search for direct detection and deeper understanding of this elusive cosmic ingredient, which holds the key to the universe's grand architecture. Through relentless innovation and unwavering curiosity, humanity marches onward, unraveling the secrets of the cosmos and expanding the horizons of knowledge with every discovery. And additionally, the process of galaxy formation and evolution is steeped in enduring mysteries. How do galaxies merge? How are stars born across the diverse galactic landscapes? And what mechanisms bring star formation to a halt in some galaxies while others blaze with stellar birth? These questions lie at the heart of one of astronomy's greatest quests. At the center of this exploration is the enigmatic phenomenon known as galactic feedback. Here, powerful forces like supernova explosions and the raging cores of active galactic nuclei unleash vast amounts of energy, reshaping their cosmic neighborhoods. These energetic outbursts generate colossal winds, driving gas out of galaxies and altering the conditions necessary for new stars to form. In doing so, they influence not only the fate of individual galaxies, but also the intergalactic medium, the vast, tenuous web of matter stretching between galaxies. To understand these cascading interactions is to begin to unravel the intricate architecture of the universe, from its smallest stellar nurseries to the sprawling filaments of the cosmic web. Scientists peering into deep space and deep time are piecing together a grand puzzle. How a near-uniform sea of primordial matter transformed into the astonishing diversity of galaxies we see today. The story begins shortly after the Big Bang. In that early universe, subtle fluctuations in the density of the primordial gas, made almost entirely of hydrogen and helium, began to grow under the relentless pull of gravity. Denser regions accumulated more mass, forming the seeds of what would become dark matter halos. These halos acted as cosmic anchors, drawing in gas that cooled and coalesced to ignite the first stars. From these ancient lights, the first proto-galaxies emerged. As the universe aged, these early galaxies collided and merged, accreting matter and evolving into the complex forms we now recognize. Galaxy collisions were not just chaotic events, they were creative forces, forging new structures and reshaping galactic identities. When two spiral galaxies collided, the outcome could be an elliptical galaxy, a vast, rounded system with older stars and a depleted reservoir of star-forming gas. These morphological transformations depended on the velocity, mass, and angle of the collisions, adding layers of complexity to the galactic saga. Today's galaxies, spiral, elliptical, and irregular, bear the scars and signatures of their histories. Spiral galaxies, like our Milky Way, emerged from environments rich in angular momentum. This momentum flattened the infalling gas and stars into a rotating disk adorned with graceful, star-forming spiral arms. In contrast, elliptical galaxies, often born of more violent mergers, exhibit smoother, more spheroidal shapes and harbor older stellar populations. Irregular galaxies defy classification. Their asymmetry often results from gravitational distortions or tidal interactions with nearby galaxies. They are the cosmic misfits, testaments to the unpredictable nature of galactic evolution. Yet, the story doesn't end there. Scientists use powerful simulations and precise observations to delve deeper into these cosmic processes. With every new discovery, they refine our understanding of how galaxies form, evolve, and interact across the vast expanse of time. Among these celestial giants, the Milky Way stands as a particularly captivating subject. With its luminous spiral arms stretching out from a densely packed central bulge, it is both a typical spiral galaxy and a unique entity. It serves as a window into the broader mechanics of galactic life, a dynamic laboratory for unraveling the secrets of the cosmos. And so, the spiral arms of our Milky Way come alive as bustling nurseries of creation. These sweeping, graceful arcs are far from mere cosmic decorations. They are vibrant regions where young, brilliant stars ignite in clusters, surrounded by glowing nebulae and swirling clouds of interstellar gas and dust. Here, the galaxy's life cycle unfolds in vivid detail, painting a dynamic portrait of birth and renewal across the celestial canvas. At the heart of this grand structure lies the galactic center, a realm dominated by the enigmatic presence of Sagittarius A Sti, a supermassive black hole with a mass some 4 million times that of our Sun. This colossal entity governs the movements of stars and matter in its vicinity, shaping the very dynamics of our galaxy's core. Its immense gravitational pull sculpts the orbits of nearby stars, acting as a cosmic anchor in a swirling sea of celestial bodies. Beyond the glowing disk, the Milky Way extends into a vast, mysterious halo. This halo stretches far beyond the stars visible to our eyes, populated by ancient stars, dense globular clusters, and an elusive substance known as dark matter. Though invisible, dark matter's gravitational influence is undeniable, holding the galaxy together and affecting the motions of stars on its outer edges. This halo, shrouded in cosmic mystery, is crucial for the stability and longevity of the Milky Way itself. Moreover, our galaxy does not drift alone through the universe. It is part of a larger community called the Local Group, a cosmic neighborhood comprising more than 50 galaxies, including the majestic Andromeda and the smaller Triangulum. These neighbors engage in a gravitational dance, their interactions pulling streams of stars and gas from smaller satellites, weaving intricate tidal tales that tell stories of cosmic encounters and mergers. Strikingly, the Milky Way defies expectations with its flat rotation curve. Instead of slowing down at the edges, stars and gas maintain a steady orbital speed far from the galactic center, a phenomenon that confounds classical physics and points decisively to the presence of dark matter. This invisible mass acts as the galaxy's unseen scaffold, a shadowy framework crucial to understanding the true nature of galaxies and the cosmos at large. Furthermore, our vantage point within the Milky Way grants astronomers an unparalleled opportunity to explore the intricacies of galactic formation and evolution. From our position inside this sprawling spiral, we can observe and unravel the history, structure, and motion of billions of stars, insights that reveal the very processes that shape not only our galaxy, but galaxies across the universe. Spiral galaxies like the Milky Way captivate with their distinct features. Their spiral arms are not rigid structures, but waves of density that ripple through the galactic disk. As gas and dust pass through these waves, they compress, sparking new waves of star formation. This makes the arms dazzling tapestries of young, hot stars that shine with brilliant blues and whites, surrounded by nebulous clouds that glow softly with the birth of new suns. In a fascinating twist, the rotational dynamics of spiral galaxies challenge our understanding of motion. Unlike planets in the solar system, where outer bodies move more slowly, stars in these galaxies orbit the center at nearly constant speeds regardless of their distance. This uniformity, manifested in the galaxy's flat rotation curve, remains one of the most compelling proofs of dark matter's presence, a mysterious force that binds galaxies together with its invisible grip. Adding to the complexity, many spiral galaxies, including our own, feature a central galactic bar, a dense, linear arrangement of stars stretching from the core into the disk. This bar exerts a profound influence on the galaxy's behavior, funneling gas and dust inward, sparking waves of star formation, and potentially feeding the supermassive black hole at the center. It is a powerful agent of change, driving the evolution of the galaxy from within. Thus, the Milky Way stands not just as a starry spectacle in the night sky, but as a living, evolving system, a cosmic symphony orchestrated by gravity, dark matter, and the relentless cycle of birth and death among the stars. It invites us to peer deeper, to explore further, and to marvel at the intricate workings of the universe itself. Finally, the grand narrative of spiral galaxies, those magnificent pinwheels of stars, is deeply entwined with their encounters across the cosmic stage. Their elegant arms, while serene from a distance, bear the chaotic fingerprints of gravitational drama. When galaxies interact, whether brushing past one another or colliding head-on, the consequences ripple through space and time. Spirals sprout features like tidal tails stretching like celestial ribbons, bridges of stars connecting galactic neighbors, and rings born from cosmic impact. These are not merely decorative scars, they are signatures of violent encounters that stir dormant gas, ignite waves of star birth, and reorder stellar populations within the spiral arms. Each twist and anomaly in their structure becomes a breadcrumb trail for astronomers, leading to a deeper understanding of galactic genesis and transformation. Elliptical galaxies, by contrast, wear a mask of simplicity. Lacking the swirling arms of their spiral cousins, they appear as smooth, luminous ellipses suspended in the dark. But beneath this placid exterior lies a web of enigmas that continue to perplex astronomers. Chief among these is the question of their origin. The long-standing theory suggests that ellipticals are the aftermath of galaxy mergers, cosmic pileups that smooth out structure and quench star formation. These galaxies, dominated by old red stars and barren of cold gas, seem to be galactic retirement homes. Yet, observations from the early universe disrupt this narrative. Some massive ellipticals appear to have assembled in astonishing haste, fully formed just a few billion years after the Big Bang, suggesting a need for faster, more exotic formation pathways. Then there's the mystery at the heart of many elliptical galaxies: supermassive black holes. These titanic objects, millions to billions of times the mass of the Sun, are tightly linked to their host galaxies through a relation known as the M-sigma correlation, tying the black hole's mass to the motion of stars around it. But why this relationship exists remains unknown. Even detecting these cosmic giants can be difficult. Unlike the feeding frenzies observed in active galactic nuclei, many elliptical galaxies show no signs of black hole activity, leaving astronomers to infer their presence only through subtle stellar dynamics. Kinematically, ellipticals defy expectation. Some rotate, others don't. Many exhibit bewildering misalignments between the way stars move and the way light is distributed. These mismatches speak to turbulent pasts, episodes of merging and upheaval that jumbled the orbits of stars. And then there's the elusive dark matter. While spiral galaxies wear their dark matter halos like clear gravitational armor, ellipticals are more cryptic. Their motions hint at dark matter, but the numbers don't always add up, hinting either at hidden complexities or flaws in our models of gravity itself. Adding to the puzzle are the faint halos of intracluster light that sometimes surround elliptical galaxies, ghostly glows from stars torn from their homes during galactic brawls. These stellar orphans drift through clusters, relics of past collisions, illuminating the violent underpinnings of cosmic evolution. Far from being relics of a simpler time, elliptical galaxies are riddled with secrets. Their mysteries challenge the boundaries of current astrophysics and remind us that the universe, even in its quietest corners, is full of stories still waiting to be told. And yet, the irregular shapes of certain galaxies, often simply labeled as irregular galaxies, tell a story far more complex than mere disorder. These cosmic oddities owe their chaotic forms largely to the dramatic forces of gravitational interactions and galactic mergers, as well as internal phenomena like explosive star formation and supernovae. Unlike the elegant spirals or smooth ellipses that characterize many galaxies, irregular galaxies exhibit wild, asymmetrical shapes that defy simple classification. When galaxies draw near or collide, their immense gravitational pulls tug at stars, gas, and dust, twisting and distorting their once familiar structures. These encounters unleash tidal forces that stretch and warp, spawning spectacular features like tidal tails, elongated streams of stars, and bridges of matter that link galaxies in a cosmic dance. Such interactions often rip gas from galaxies, fueling frenzied bouts of star formation that scatter brilliant star clusters across the chaotic landscape, further contributing to their disorderly appearance. And supernova explosions add yet another layer of complexity. These titanic stellar deaths inject tremendous energy into the surrounding gas, carving bubbles, driving shock waves, and hurling material in unpredictable directions. The result is an interstellar environment roiling with turbulence, shaping the galaxy's morphology into a patchwork of irregular clumps and voids. Some irregular galaxies are thought to be caught mid-transformation, still assembling or shedding matter, unsettled by internal instabilities or their relatively low gravitational grip compared to their more massive cousins. Their varied, often turbulent appearances embody the universe's ceaseless dynamism, serving as living records of galaxy evolution's most violent and transformative processes. Looking ahead, the impending collision between the Andromeda Galaxy and our own Milky Way looms as one of astronomy's greatest puzzles. Set to unfold in roughly 4 to 5 billion years, this colossal event holds many uncertainties. The timing, shaped by the galaxy's velocities and trajectories, remains approximate. What will emerge from their cosmic embrace? Simulations hint at the birth of a massive elliptical galaxy, sometimes dubbed Milkomeda, but the exact structure and characteristics of this new galactic entity remain speculative. Amidst these grand galactic shifts lies a more purse string, the fate of our solar system. Will it be cast outward into the far reaches of the merged galaxy or pulled closer to the newly formed galactic core? The gravitational turmoil will send stellar orbits into flux, altering cosmic neighborhoods over millions of years. Meanwhile, the collision's fierce compression of gas clouds promises a spectacular surge in star formation, igniting new generations of stars in a final celestial fireworks display. In this cosmic saga, irregular galaxies and galactic collisions reveal the universe not as a static tableau, but as an ever-changing arena where gravity and chaos sculpt the grandest of cosmic masterpieces. But the scale and duration of this starburst phase remain cloaked in uncertainty. Scientists, driven by curiosity and the relentless pursuit of cosmic understanding, are especially eager to unravel the influence of the supermassive black holes nestled at the heart of both galaxies, Sagittarius A star in the Milky Way, and the mysterious colossus at the core of Andromeda. These cosmic giants are not merely passive spectators in the galactic ballet. They are expected to spiral inward and merge, releasing powerful gravitational waves that could ripple across the very fabric of spacetime. Yet, the precise choreography of this gravitational dance, the timing, the dynamics, the aftershocks, remains one of the great puzzles in astrophysics. This profound uncertainty underscores the dynamic and ever-evolving nature of galactic transformation. It is this unknown, this cosmic blank page, that propels astronomers to simulate, model, and observe, striving to predict the destiny of the Milky Way-Andromeda collision. As these two spiral titans hurtle toward one another over billions of years, they offer an unprecedented window into the forces that shape galaxies, through mergers, interactions, and gravitational entanglements. Galactic evolution, the sweeping story of how galaxies form, change, and sometimes collide, is riddled with enigmas that continue to captivate scientific minds. One of the deepest mysteries lies in the birth of the first galaxies after the Big Bang. The LCDM model, lambda cold dark matter, provides a powerful scaffold, suggesting that minute fluctuations in the early universe's density seeded the formation of cosmic structures. But the specifics, the actual pathways by which the earliest galaxies emerged, some within just a few 100 million years of the Big Bang, elude our full understanding. Observations of these ancient galaxies often reveal levels of complexity and rapid development that defy the predictions of existing models. Equally mysterious is the role of supermassive black holes in this cosmic narrative. These gargantuan objects, anchoring the centers of most massive galaxies, appear to be more than silent sentinels. They may actively shape their host galaxies, regulating star formation through powerful jets and energetic feedback loops. The M-sigma relation, linking a black hole's mass to the velocity dispersion of stars in the galaxy's bulge, hints at a deep underlying connection. Yet, we don't fully grasp whether black holes guide galactic growth, or respond to it, or evolve in parallel through a more complex interplay. Dark matter, the unseen scaffolding of the universe, adds yet another layer to this intricate puzzle. While we know it plays a critical role in galaxy formation, clustering, and the shaping of large-scale cosmic structures, its true nature remains elusive. How does dark matter interact, if at all, with ordinary matter? How does it influence the internal dynamics of galaxies, particularly the faint and enigmatic dwarf galaxies, where dark matter dominates? These are questions that continue to challenge and redefine cosmological theory. And then there are the galactic collisions, mergers and interactions that are both destructive and creative. These events can trigger frenzies of star formation and dramatic structural changes, transforming elegant spiral galaxies into featureless ellipticals. Yet the final outcome of such interactions depends on a ballet of variables: mass ratios, orbital trajectories, relative velocities, and the timing of impact. Advanced simulations offer glimpses into these possibilities, but the complexity of real-world physics ensures that many aspects remain veiled in uncertainty. As we peer deeper into the cosmos, we are not just looking outward, we are looking forward, attempting to foresee the fate of our own galaxy in the grand chronicle of the universe. The future merger of the Milky Way and Andromeda is not only a spectacular event, it is a key to unlocking the deepest secrets of how galaxies live, die, and transform. Lastly, the impact of environmental factors, such as a galaxy's position within a cluster or its interactions with the intergalactic medium, adds another unpredictable dimension to our understanding of galactic behavior. In the bustling neighborhoods of dense galaxy clusters, galaxies are not isolated. They are buffeted, stripped, and reshaped by their surroundings. One such process, ram pressure stripping, acts like a cosmic wind tunnel, sweeping away a galaxy's reservoir of star-forming gas as it plows through the intracluster medium. The result? A sudden halt in star formation. This dramatic quenching effect paints a broader picture of how environment sculpts galactic destiny. But the story doesn't end there. How these environmental mechanisms interact, compete, or collaborate to sculpt the diverse forms and life cycles of galaxies across different regions of the universe remains one of the most compelling puzzles in modern astrophysics. It is here, in this chaotic cosmic interplay, that astronomers seek answers that may redefine our understanding of galaxy evolution itself. These mysteries underscore an urgent need: more precise observations, more powerful simulations, and sharper theoretical tools to unveil the hidden workings of galaxies. And within this grand narrative lies the beating heart of galactic evolution: star formation. The birth of stars, triggered within the dense, cold folds of molecular clouds, is a process both beautiful and baffling. While scientists agree that gravity plays the lead role, collapsing pockets of gas into newborn stars, the opening act is still shrouded in mystery. What ignites this gravitational cascade? Turbulence rippling through the gas, magnetic fields threading through the clouds, or perhaps the explosive shockwaves from dying stars, supernovae spurring new life from the ashes? The truth is likely a complex dance of all these forces, and uncovering the details remains a cornerstone quest for astrophysicists. Then there's the enigma of massive star formation. These giants, more than 8 times the mass of our sun, are paradoxical beings. Their fierce radiation and violent stellar winds should, by all accounts, blow away the very material they need to grow. Yet, they do form, and they do so quickly and in great numbers. Theories suggest that disk accretion, where matter spirals in through a rotating disk, or competitive accretion within tightly packed stellar nurseries, might help explain their birth. Still, the observational evidence remains incomplete, leaving the formation of these cosmic titans a riddle begging for resolution. And behind every newborn star is a deeper pattern, the initial mass function, or IMF. This statistical blueprint describes how many stars of various masses emerge from a cloud. Universally, it seems to favor the small and faint over the massive and bright. But why? What governs this distribution, and does it shift across different cosmic environments? These questions have far-reaching implications, influencing everything from galactic dynamics to the chemical makeup of the universe. Even magnetic fields, invisible yet pervasive, add another twist. They thread through molecular clouds, perhaps resisting gravitational collapse in some regions while guiding matter in others. But mapping these magnetic forces and deciphering their role in shaping star formation is an observational feat few instruments can yet achieve. Their subtle fingerprints on the cosmos remain one of the last great frontiers in our exploration of the stellar cradle. Together, these questions form a constellation of unknowns, each a vital piece in the grand puzzle of cosmic evolution. And feedback processes from young stars, like stellar winds, radiation pressure, and supernova explosions, play a monumental role in shaping the universe. These powerful forces can ignite new waves of star formation by compressing nearby gas clouds, sparking fresh cosmic creation. Yet, paradoxically, they can also hinder star birth by dispersing the very material needed for new stars to emerge. Striking a delicate balance between these opposing effects is one of astronomy's greatest puzzles, as scientists strive to understand how these feedback mechanisms govern star formation rates in vastly different cosmic environments. Moreover, the birth of planetary systems alongside their stars adds layers of complexity to this grand story. The evolution of protoplanetary disks, the swirling disks of gas and dust encircling young stars, gives rise to planets through an intricate dance of gravity and dynamics. These processes, filled with unknowns, weave a tale still being pieced together by astronomers. From the initial triggers that spark star formation to the mysterious influences of magnetic fields and the initial mass function, every stage unfolds with awe-inspiring complexity. Continuous breakthroughs in observational technology, theoretical modeling, and computational simulations are essential to illuminate these cosmic mysteries. As we gaze at the night sky, each star, unique in mass, temperature, and brightness, beckons with its own secrets. Take neutron stars, for example. These incredibly dense remnants of supernovae cram a sun's worth of mass into a sphere barely 12 miles across, wielding magnetic fields trillions of times stronger than Earth's. Many reveal themselves as pulsars, emitting rhythmic beams of radiation that challenge our understanding of matter under extreme conditions. When neutron stars collide, they send ripples through space-time, gravitational waves that we can detect here on Earth, opening new windows into the violent ballet of the cosmos. Then there are black holes, the enigmatic stellar corpses so dense that not even light can escape their grasp. These cosmic enigmas often reveal themselves only through their interactions with nearby matter, or through gravitational lensing, where their intense gravity bends the path of light itself. Ranging from stellar mass black holes to the supermassive giants lurking at the hearts of galaxies, they push the boundaries of our understanding of gravity and quantum mechanics. Questions abound. How exactly do they form? What transpires at the event horizon, the point of no return? And how do these colossal forces shape the galaxies they inhabit? Supermassive black holes, in particular, wield profound influence over galaxy evolution. Yet the details of this cosmic interplay remain elusive. Driven by such questions, astronomers and physicists relentlessly push the limits of technology and theory in pursuit of answers. And supernovae, the spectacular cataclysmic deaths of stars, serve as cosmic fireworks that light up the universe with their brilliant explosions. These cataclysms scatter the elements forged in stellar hearts: carbon, oxygen, iron, seeding the cosmos with the raw materials for new stars, planets, and ultimately, life itself. Each supernova writes a chapter in the grand saga of the universe's ongoing creation, reminding us of the awe-inspiring cycles of destruction and rebirth that shape everything we see above. And yet, one of the most captivating enigmas in modern astrophysics lies in the spectacular demise of stars, the supernova. These cosmic cataclysms mark the final act in the life of a massive star, and at the heart of this violent end is a process that scientists still struggle to fully comprehend. Core collapse supernovae, for instance, erupt when a giant star runs out of nuclear fuel, its core collapsing under gravity's relentless grip. Temperatures soar, pressures climb to unimaginable heights, and a series of nuclear reactions ignite in a cosmic furnace. But despite decades of research, including elaborate simulations and sophisticated theoretical models, one essential question persists. How exactly does the collapsing core ignite a shockwave powerful enough to blow the star apart? This explosion, blazing across galaxies, gives birth to some of the most mysterious and extreme objects in the universe: neutron stars or black holes, depending on the star's original mass. Yet the metamorphosis from imploding core to ultra-dense remnant remains wrapped in uncertainty. The mechanisms, the transition, even the very physics may still be eluding us. Then there's the intriguing phenomenon of type Ia supernovae. These aren't born from collapsing giants, but from a quiet white dwarf in a binary system. As it draws material from its companion star, it reaches a critical mass, triggering a thermonuclear runaway. These explosions, used as standard candles to measure vast cosmic distances, are cornerstones of our understanding of the universe's expansion, and yet their precise origins, variations, and triggering conditions continue to provoke scientific debate. To decode these stellar explosions is to open a window onto the universe itself. From the distribution of elements in space to the very fabric of spacetime shaped by matter under extremes of pressure and temperature, every supernova is a beacon of insight. A fleeting flare of light, visible across light years, offering data that could reshape cosmology. Neutron stars, the dense remnants left behind by supernova, are in a league of their own. In these stellar corpses, matter is crushed to extremes, so dense that a sugar cube-sized portion would weigh as much as a mountain. Here, under immense pressure and heat, atoms are stripped apart and reassembled in exotic forms. Some theories suggest a core composed of not just neutrons, but perhaps even quark-gluon plasma or other exotic states of matter that defy replication on Earth. Among the most mysterious neutron stars are magnetars, whose magnetic fields are trillions of times stronger than Earth's. These titanic forces can warp the star's crust, causing starquakes that release massive bursts of radiation. The origin and maintenance of such staggering magnetic fields remain one of astrophysics' most compelling puzzles. Then come pulsars, neutron stars spinning at incredible speeds, some rotating hundreds of times per second. As they spin, they emit beams of electromagnetic radiation from their magnetic poles. When these beams sweep past Earth, we observe them as rhythmic pulses, like celestial lighthouses ticking across the sky with astonishing regularity. What's most extraordinary is the precision of this timing. Despite being immersed in environments of crushing gravity and intense magnetism, pulsars maintain remarkably stable rotation. Their structure, compact, massive, nearly impervious to disturbance, keeps them spinning like finely tuned gyroscopes. The emission pattern remains fixed relative to the spin axis, creating a regular beat detectable over years, even decades. This near-perfect timing turns pulsars into cosmic clocks. As they gradually lose energy through radiation and particle winds, their spin slows, but even this deceleration is predictably smooth. By tracking this slowdown, astronomers can glean insights into gravitational waves, test the limits of general relativity, and explore the properties of matter at densities that challenge our most advanced physics. Each neutron star, each pulse of radiation, and each supernova explosion tells part of a story still being written. A story of fire, collapse, and rebirth in the deepest, darkest corners of the universe. And yet, hidden within the silence of deep space, a cosmic metronome ticks with unimaginable precision. These are pulsars, rapidly spinning neutron stars emitting beams of electromagnetic radiation. They act like celestial timekeepers, their rhythmic pulses so regular that even the slightest deviation can speak volumes. Any irregularity in their timing could be a whisper from an unseen planet or a ripple in space-time caused by the passage of gravitational waves. Such minuscule changes offer scientists a powerful way to peer into the invisible mechanics of the cosmos. The study of pulsars has evolved far beyond the realm of exotic astrophysical curiosities. Today, they are indispensable tools, natural laboratories where the laws of physics are put to the ultimate test. They help refine Einstein's general theory of relativity and may even herald the first glimpses of gravitational waves from the early universe. By mapping the pulses, we are charting a new frontier in cosmic exploration, one that fuses observation with theory to reveal hidden structures and events far beyond the reach of our telescopes. Black holes, on the other hand, are the enigmatic destinations of stellar death. When a massive star burns through its nuclear fuel, it collapses under its own gravity, leaving behind an entity so dense and powerful that not even light can escape. These are not just stellar remnants, they are cosmic paradoxes that push the very boundaries of human understanding. One of the most profound mysteries they present lies at the event horizon, the invisible boundary that surrounds a black hole. Cross it, and information is seemingly lost forever. This defies the tenets of quantum mechanics, which assert that information cannot be destroyed. This apparent contradiction has ignited one of the most significant debates in modern physics, known as the information paradox, a problem that continues to baffle scientists and philosophers alike. And what of the singularity, the theoretical heart of a black hole, where density becomes infinite and space-time itself warps into a point of no return? General relativity breaks down here, and quantum theory has yet to offer a complete replacement. A unified theory of quantum gravity remains elusive, but its discovery could rewrite the foundations of physics and offer answers to some of the universe's deepest riddles. The formation of black holes also remains a captivating puzzle. Do they arise solely from supernova explosions, or can massive stars in crowded stellar nurseries collapse directly into these dark giants without a fiery finale? Observations now suggest that black holes of immense mass, millions to billions of times greater than our sun, reside at the hearts of most galaxies. How they formed and grew is still a matter of speculation. Did smaller black holes merge to form the titans we observe today? Or did they emerge fully formed from the earliest epochs of the universe? Gravitational wave detections, ripples in space-time from colliding black holes, have begun to offer new clues, providing a new lens through which we can observe these cosmic collisions. But with every new discovery, new questions arise. How did these binary systems form? How did they spiral into one another in a cosmic dance that ended with a thunderous silence? Black holes, pulsars, gravitational waves, these are not isolated wonders. They are the keys to understanding the universe's deepest structures and oldest truths. They confront us with paradoxes, inspire new physics, and draw the gaze of science ever further into the void. And yet, another profound mystery haunts the realm of astrophysics: the black hole information paradox, a cosmic enigma brought to prominence by the legendary Stephen Hawking. It begins with a fundamental contradiction between the two great pillars of modern physics, general relativity and quantum mechanics. According to Einstein's theory, anything that crosses the event horizon of a black hole, the point of no return, is irretrievably lost to the outside universe. Matter, energy, and most disturbingly, information all vanish into the abyss beyond our grasp forever. But quantum mechanics protests. In this framework, information is sacred. It cannot be destroyed, even if the particles it describes are scattered or transformed. This conflict becomes even more perplexing with Hawking's own groundbreaking contribution, Hawking radiation. This phenomenon suggests that black holes are not eternal. They emit radiation and slowly evaporate over time. And with their final whisper into the void, the question looms: if the black hole vanishes, where does the information go? This paradox isn't just an academic quibble. It strikes at the heart of how we understand the universe. If information can disappear, then quantum theory itself may be incomplete, or worse, fundamentally flawed. Yet, no clear resolution has emerged. Theoretical physicists propose solutions ranging from holographic principles to the idea of firewalls, yet none are universally accepted. Adding to the cosmic puzzle is the baffling existence of supermassive black holes, gargantuan behemoths millions or even billions of times more massive than our sun. We find them lurking in the hearts of galaxies, including our own Milky Way. But how did they form so quickly in the early universe? The timeline doesn't add up. Theories abound. Perhaps they were born from the direct collapse of massive gas clouds or through the merger of smaller black holes. But each model carries unanswered questions and scant observational support. Even the event horizon, the edge of a black hole, remains shrouded in mystery. What truly happens to particles and information as they approach this invisible boundary? Do they freeze in time? Do they dissolve into a holographic projection? Or are they somehow preserved in a form we have yet to comprehend? These are not idle curiosities. They are active frontiers of physics, driving new theories, instruments, and explorations. Black holes, once the stuff of speculative fiction, now sit at the center of our deepest inquiries into reality. They are not merely celestial phenomena. They are keyholes into the structure of space, time, and the quantum fabric of everything. Their formation, especially in the case of stellar mass black holes, begins with the spectacular deaths of massive stars. When a star more than 20 times the mass of our sun burns through its nuclear fuel, it can no longer resist its own gravity. The core collapses, and if the remaining mass is sufficient, it compresses into a singularity, an infinitely dense point sealed within an event horizon. The physics of this collapse is still not fully understood. Neutron degeneracy pressure, neutrino interactions, and turbulent instabilities all play roles in the final moments. How exactly does a star die to become a black hole? We're still uncovering the details, and yet the giants remain most elusive. Supermassive black holes likely did not form from stars at all. Their origin story is different, perhaps seeded by primordial structures in the early universe, or arising from vast clouds of gas collapsing directly into darkness. Unlike stellar black holes, their birth and growth are tethered not to singular supernovae, but to galactic evolution itself. In the end, black holes may be our most powerful tools for unlocking the universe's secrets. Through them, we glimpse a reality where time distorts, matter warps, and the known laws of physics strain and crack. They are the universe's most extreme laboratories, and we are only beginning to read their results. But through a combination of cosmic processes that unfolded in the early universe, the origins of supermassive black holes remain one of astrophysics' most tantalizing enigmas. Some hypotheses suggest that these colossal objects emerged gradually, growing from mergers of smaller black holes, swelling as they fed on immense reservoirs of gas and dust. Others propose a far more dramatic birth, the direct collapse of massive primordial gas clouds, bypassing the life and death of stars entirely. Yet the mystery deepens. Observations of quasars, blindingly luminous active galactic nuclei, reveal that some of these supermassive black holes were already in place less than 1 billion years after the Big Bang. Their sheer mass and early appearance defy our conventional models of cosmic evolution, hinting at powerful and possibly unknown mechanisms of rapid growth. The story doesn't end there. Black holes are anything but static. As they interact with their surroundings, they evolve, devouring nearby matter, merging with others of their kind, or being flung into motion by gravitational tides and stellar encounters. These feeding frenzies often light up the cosmos. As gas spirals inward, it forms an incandescent accretion disk, heating to extreme temperatures and unleashing torrents of radiation. In some cases, black holes erupt with relativistic jets, beams of particles moving near light speed, stretching thousands of light years into intergalactic space. Additionally, the advent of gravitational wave astronomy has given us a new way to eavesdrop on the universe. Each detection of a black hole merger captures the final violent moments before two titanic masses coalesce, offering insight into their masses, spins, and the nature of gravity itself. These events are not just cosmic fireworks, they are vital clues in decoding the black hole life cycle. As our telescopes grow sharper and our theories more refined, black holes are beginning to surrender their secrets. But the cosmos still holds many locked doors. Black holes exist in various forms, each one a puzzle. Stellar mass black holes, born from the deaths of massive stars, are the most familiar, yet they harbor mysteries of their own. What lies within the event horizon? General relativity predicts a singularity, a point of infinite density, but quantum mechanics suggests a different story, involving exotic states of matter and unknown physics. Then there are intermediate mass black holes, elusive entities theorized to weigh in at thousands to hundreds of thousands of solar masses. They could represent the missing evolutionary link between stellar mass and supermassive black holes. But they are vanishingly rare in our observations, their origins obscured. Are they the products of countless stellar mergers? Or do they arise from entirely different phenomena inside dense star clusters? and towering above them all are the supermassive black holes anchoring the hearts of galaxies. Their rapid growth in the early universe remains one of the most profound puzzles in astrophysics. How could some of them reach billions of solar masses so soon after the Big Bang? Are we missing key mechanisms of mass acquisition, or were their initial seeds far larger than we've imagined? In this vast cosmic arena, black holes are not just endpoints of matter, they are windows into the fundamental workings of reality itself. With each new observation, we are drawn deeper into their story, compelled by the promise that understanding them might finally reveal the universe's most closely guarded truths. Additionally, the environments surrounding supermassive black holes, often characterized by swirling accretion disks and powerful relativistic jets, are among the most complex and enigmatic regions in the cosmos. These areas blaze with incredible energy and dynamism, yet the underlying physics that governs the interplay between the black hole, its accretion disk, and the magnetic fields threading through space remains a frontier of scientific inquiry. Each black hole, whether stellar mass or supermassive, reveals a unique facet of the universe's dark heart, holding tantalizing clues to the fundamental forces and processes that shape everything we see. Beyond the event horizon, the boundary marking the point of no return, lies a realm that challenges our very understanding of reality. This invisible threshold is where gravity's grip becomes so intense that not even light can escape. Crossing this boundary means stepping into a domain where conventional notions of space and time unravel. One of the most profound mysteries is the singularity nestled at the black hole's core, a point where, according to Einstein's general relativity, matter is compressed to infinite density and the fabric of space-time contorts infinitely. Here, the laws of physics as we know them collapse, pushing our theories to their breaking point and demanding a revolutionary framework that unites gravity with quantum mechanics. The enigma of what happens to information swallowed by a black hole adds another layer to this cosmic puzzle. Known as the information paradox, this problem arises from a clash between the principles of general relativity and quantum mechanics. Quantum theory insists that information about physical states can never be destroyed, yet the irreversible nature of the event horizon suggests otherwise. The groundbreaking insight by Stephen Hawking that black holes can emit faint radiation and eventually evaporate further complicates this paradox. If black holes vanish over time, does the information they devoured disappear with them? This question remains one of the most tantalizing unsolved problems in physics, inspiring bold hypotheses such as the holographic principle, which proposes that all the information inside a black hole might be encoded on its surface, and the firewall theory, which posits a blazing barrier incinerating information at the horizon. Delving deeper, the internal structure of black holes defies simple imagination. Far from being mere spheres of darkness, rotating black holes, known as Kerr black holes, are theorized to harbor intricate inner regions, including multiple event horizons and zones where space-time itself is twisted by immense rotational forces. These theoretical constructs hint at exotic possibilities, wormholes, cosmic shortcuts that might link distant parts of the universe or even other universes. Though speculative, such ideas stretch the boundaries of our understanding and spark wonder about what lies beyond. The connection between black holes and thermodynamics offers yet another fascinating dimension. The work of Jacob Bekenstein and Stephen Hawking revealed that black holes possess entropy proportional not to their volume, but to the area of their event horizon. This remarkable discovery suggests profound insights into the nature of space-time, hinting that gravity and thermodynamics are intertwined in ways we are just beginning to grasp. If black holes obey thermodynamic laws, what does this reveal about the fundamental fabric of the cosmos? At the core of all these mysteries is the singularity itself, a cosmic paradox that defies explanation. Here, gravitational forces become so extreme that the usual rules governing space and time no longer hold. This extreme condition demands a unified theory of quantum gravity, one capable of reconciling the macroscopic realm of relativity with the microscopic world of quantum mechanics. Leading contenders like string theory and loop quantum gravity offer promising frameworks. String theory imagines the universe's fundamental particles as tiny vibrating strings that might smooth out singularities, while loop quantum gravity envisions space-time as a granular fabric, avoiding infinite densities. These theoretical advances not only aim to describe singularities, but also confront the deep puzzle of the information paradox. Resolving this conflict could revolutionize physics, reshaping our understanding of reality itself. Ideas such as the holographic principle, which posits that all information within a volume of space can be described by data on its boundary, hint at an astonishing unity between gravity, quantum mechanics, and information theory. The true nature of black hole singularities remains one of the most profound and elusive frontiers in modern science. As we push the boundaries of observation and theory, these cosmic enigmas beckon us toward new discoveries that promise to reshape our understanding of the universe's most fundamental laws, illuminating the dark heart of reality itself. And yet, in the heart of our universe, black holes reign as enigmatic architects, massive, invisible titans shaping their surroundings in ways that stretch the limits of human comprehension. Their influence is not merely gravitational, it is a symphony of forces, interactions, and unknowns that continue to astonish the scientific community. A focal point of this cosmic choreography is the process of accretion. As gas, dust, and stellar remnants spiral into the gravitational maw of a black hole, they form a glowing disk, an accretion disk, heated to such extremes that it radiates more energy than entire galaxies. It's a dramatic display of power, but one still shrouded in mystery. How does matter lose its angular momentum? What role do magnetic fields play in orchestrating this violent ballet? And how are colossal high-speed jets, some stretching for thousands of light years, launched from these regions with such precision and fury? These relativistic jets aren't just spectacular, they're influential. By plowing through interstellar space, they can trigger or suppress star formation, regulating the very structure of galaxies. Yet the physical laws governing their emergence remain elusive. Scientists suspect that magnetic fields wound tightly in the accretion disk might act as cosmic engines, channeling energy outward, but the full picture remains a puzzle. Another layer of intrigue lies in the deep-rooted connection between supermassive black holes and the galaxies that host them. At the center of most galaxies lurks a black hole millions or even billions of times more massive than our Sun. And curiously, there's a clear correlation between the mass of these black holes and the velocity of stars in the galactic bulge, a phenomenon known as the M-sigma relation. This suggests a feedback loop, a kind of cosmic regulation where black holes influence and are influenced by the evolution of their host galaxies. How does this feedback work? One compelling theory posits that energy expelled during accretion heats and expels gas, quenching star formation and thus governing galactic growth. But the timing, scale, and efficacy of such feedback mechanisms are still poorly understood, especially across the myriad stages of galactic evolution. Enter gravitational waves, the faint murmurs of space-time itself, stirred by the merging of black holes. These waves are unlocking new vistas of astronomical observation, offering a glimpse into events previously hidden in darkness. But as with all things black hole, they present new questions. How often do these mergers occur? What can they tell us about the hidden population of black holes scattered across the cosmos? And could the waves themselves, as they ripple through the fabric of space-time, influence their surroundings in subtle, undetected ways? Then there's the phenomenon of black hole spin, a twist of fate where the very rotation of a black hole drags space-time along with it, a process known as frame dragging. This bizarre distortion warps the orbits of nearby objects and contorts the accretion disk itself, affecting how matter falls in and energy is ejected. Yet, the precise dynamics remain a frontier of high-energy astrophysics. Taken together, these mysteries underscore a profound truth. Black holes are not silent tombs of collapsed stars. They are dynamic central actors in the cosmic drama, shaping galaxies, stirring the interstellar medium, and possibly rewriting the rules of physics as we know them. As our tools improve and our theories evolve, we edge closer to unraveling their secrets. But for now, black holes remain both the gatekeepers of the unknown and the engines of revelation in our ever-expanding universe. Yes, We can observe black hole mergers, and these cosmic collisions are unveiling mysteries that stretch the limits of our understanding of the universe. One of the most remarkable breakthroughs in astrophysics came with the detection of gravitational waves, subtle ripples in the fabric of spacetime predicted by Einstein's general theory of relativity. First captured by the Laser Interferometer Gravitational Wave Observatory LIGO in 2015, these waves heralded a new era of cosmic exploration. And it is through these gravitational waves that we glimpse the titanic clashes of black holes, some of the universe's most violent and enigmatic phenomena. The merger of two black holes sends ripples racing across the cosmos, signals that LIGO and its European counterpart, Virgo, have been tirelessly tuning into. These observations have already revealed key insights, the masses, spins, and mysterious birthplaces of these shadowy giants. Yet profound questions remain. How do these black hole pairs come to be? Are they born together as massive binary stars that eventually collapse in tandem? Or do they form later, pulled together by gravitational forces in dense stellar environments like globular clusters? Each scenario paints a different cosmic portrait, influencing the frequency and nature of the mergers we observe. The alignment of the black hole's spins acts as a cosmic fingerprint, hinting at their origin story, whether as lifelong partners or as chance encounters forged in crowded star cities. Moreover, the aftermath of these mergers opens another window into the unknown. When black holes collide, they merge into a more massive singular entity, releasing gravitational waves that carry away energy and angular momentum. This newborn black hole undergoes a ring-down phase, settling into stability while echoing faint signals that could reveal its internal structure. Decoding these ring-down signatures remains a frontier of research, one that could test Einstein's theory in the universe's most extreme conditions and even provide clues toward the elusive realm of quantum gravity. Intriguingly, these cosmic events might also whisper through electromagnetic signals. While black holes themselves emit no light, interactions with surrounding matter before or after a merger could spark flashes, such as gamma-ray bursts, detectable by telescopes. Confirming these electromagnetic counterparts would ignite the promise of multi-messenger astronomy, weaving together gravitational and electromagnetic observations to paint a richer tapestry of cosmic events. And on the grandest scale, black hole mergers could unlock secrets about dark matter itself. Some theories propose that primordial black holes, ancient relics born in the universe's infancy, may make up a portion of dark matter. By studying the mass and distribution of merging black holes, scientists hope to test this tantalizing possibility, potentially reshaping our understanding of the cosmos's fundamental makeup. These mysteries turn black hole mergers into more than mere astronomical phenomena. They are cosmic puzzles, challenging our knowledge and inviting us to explore deeper truths. Each detected ripple brings us closer to answers that could redefine astrophysics and cosmology, revealing the universe in ways we have only just begun to imagine. And as we sharpen our detection tools and deepen our theoretical frameworks, the cosmic mysteries unleashed by these titanic collisions continue to captivate and puzzle scientists around the globe. Hawking radiation, first theorized by physicist Stephen Hawking in 1974, shakes the very foundations of our understanding of black holes and the physical laws that govern them. Classical general relativity holds that nothing, no particle, no light, can escape the clutches of a black hole once it passes the event horizon, the point of no return. Yet Hawking's groundbreaking insight proposed something radically different. Black holes are not the eternal, inescapable voids we imagined. Instead, they can emit a faint glow of radiation, born from the strange interplay of quantum mechanics at the brink of the event horizon. In this bizarre quantum theater, pairs of particles and antiparticles spontaneously spring into existence from the vacuum of space. Normally, they annihilate each other almost instantly, vanishing without a trace. But near a black hole's edge, the script changes. One particle may plunge into the black hole, trapped forever, while its partner escapes into the cosmos. To an outside observer, this escaping particle looks like radiation emitted by the black hole itself. Over time, this subtle leak of energy causes the black hole to lose mass, slowly evaporating away, a slow cosmic death foretold by quantum theory. Yet this revelation carries a profound puzzle, the information paradox. Quantum mechanics insists that information about a system's state cannot be destroyed, a principle known as unitarity. But if a black hole vanishes completely through Hawking radiation, what happens to the information about everything it swallowed? It appears to vanish too, a contradiction that suggests a fundamental rift between the pillars of modern physics, general relativity and quantum mechanics, demanding new theories or radical revisions. Moreover, Hawking radiation breathes thermodynamics into black holes, assigning them temperature and entropy. Surprisingly, a black hole's entropy is not related to its volume, but to the surface area of its event horizon, a discovery that hints at a deep, hidden connection weaving together gravity, thermodynamics, and quantum theory. This link opens a gateway to the mysterious microscopic states underlying black hole entropy and beckons physicists toward a quantum theory of gravity that unites these realms. These insights extend far beyond black holes themselves. They influence our understanding of the universe's fate, especially for small black holes that might evaporate completely over cosmic timescales. Theorists speculate that primordial black holes born in the universe's earliest moments could still be evaporating today, offering clues to unexplained astrophysical phenomena or even the nature of dark matter. While direct evidence of Hawking radiation remains elusive, future advances in detection technology promise indirect glimpses that could confirm Hawking's revolutionary vision. This radiation remains a beacon for theorists striving to reconcile the great divide between quantum mechanics and general relativity, pushing humanity toward a more unified understanding of the cosmos. Dark matter, an equally enigmatic cosmic player, comprises about 27% of the universe's total mass and energy. Yet, unlike the stars, gas, and dust that light up our telescopes, dark matter refuses to interact with light. It neither emits, absorbs, nor reflects electromagnetic radiation, making it invisible to conventional astronomical observations. Instead, we infer its presence solely through its gravitational influence on visible matter, radiation, and the large-scale structure of the universe. The dark matter mystery emerged from puzzling observations. In the 1970s, astronomer Vera Rubin unveiled a startling truth. The outer regions of galaxies spin at speeds that defy Newtonian expectations based on visible matter alone. Without some hidden mass exerting extra gravity, galaxies would tear themselves apart. This unseen substance, dark matter, was hypothesized to hold galaxies together like a cosmic glue. Further evidence comes from gravitational lensing, where massive objects bend the light of distant stars and galaxies. The amount of bending often exceeds what visible matter can explain, reinforcing the presence of vast amounts of dark matter lurking unseen. But why is dark matter so elusive? Its nature may lie in its ghostly interactions. It primarily communicates through gravity and perhaps weak nuclear forces, but it does not engage with electromagnetic forces, the very channel that reveals ordinary matter's luminous glow. This silence in the electromagnetic spectrum makes dark matter one of the greatest unsolved enigmas in astrophysics, an invisible architect shaping the universe, yet stubbornly beyond our direct sight. And this lack of interaction with light and the full spectrum of electromagnetic radiation makes dark matter one of the most elusive components of the cosmos. Traditional telescopes can't see it. Our most advanced electromagnetic detectors on Earth can't catch it. Still, scientists are not deterred. Across the globe, an array of ambitious experiments is underway, not to see dark matter directly, but to catch it in the act of influencing the matter we do see. Why then is dark matter so elusive? The core of the mystery lies in our ignorance of its true nature. Multiple theories exist. Some propose that dark matter might consist of weakly interacting massive particles, WIMPs. Others suggest axions or sterile neutrinos. Each of these hypothetical particles behaves in unique ways, requiring customized experiments to hunt them. WIMPs, for example, are thought to be far more massive than protons and interact via the weak nuclear force. If such particles exist, they might just reveal themselves in underground detectors, silent vaults of science that lie deep beneath the Earth's surface, shielded from cosmic interference. But particle candidates aren't the only possibility. Some physicists propose that dark matter could be something altogether different, perhaps primordial black holes or exotic non-particle constructs born in the earliest moments of the universe. These ideas stretch the boundaries of physics, introducing new challenges and uncertainties that redefine what detection even means. What we do know is that dark matter is not just a curiosity, it's foundational to the structure of the universe. Its gravitational pull is the hidden architecture of the cosmos, a silent scaffold around which galaxies form and evolve. Without it, the grand structures we see in the night sky would collapse or scatter. Understanding dark matter isn't optional. It's essential if we are to truly grasp the forces that shape the universe. So, how do we search for something we can't see? One promising route is indirect detection. This method doesn't look for the particles themselves, but for the cosmic fingerprints they might leave behind. Gamma rays, cosmic rays, or neutrinos generated when dark matter particles annihilate or decay. The Fermi Gamma Ray Space Telescope scans the heavens, watching for excess gamma radiation near dense regions like the galactic center, places dark matter may lurk in abundance. On the ground, telescopes such as Veritas use Cherenkov radiation to detect similar energetic events. Meanwhile, direct detection experiments dig deep into the Earth. Beneath layers of rock and soil, far from the noisy signals of the surface, lie vast detectors filled with noble gases like xenon or argon. Here, scientists wait in silence. If a dark matter particle brushes past a nucleus in one of these detectors, it may cause a faint but measurable recoil, a fleeting signature of an invisible visitor. Experiments like Lux, Lux Zeppelin, LZ, and Xenon 1T are at the forefront of this quiet chase. Another battleground is the realm of high-energy physics. At CERN's Large Hadron Collider, scientists smash protons together at near light speed. The hope that in the chaotic aftermath, dark matter particles might be born. They would not be seen directly, they would slip past detectors like ghosts, but physicists would recognize the imbalance they leave behind, a telltale loss of energy and momentum. Beyond the labs, the universe itself offers clues. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, carry imprints of dark matter's role in the infant universe. By analyzing this radiation, cosmologists piece together a picture of a cosmos where dark matter was already shaping the distribution of matter long before the first stars were born. Dark matter remains unseen, untouched, unknown. But it's not unimportant. It is a cornerstone of the cosmic story, its mass felt in the way galaxies spin, its presence inferred in the way the universe grows. To understand dark matter is to understand the very fabric of reality. From the Planck satellite, we have witnessed a revolution in our understanding of the cosmos. It provided extraordinarily precise measurements of the cosmic microwave background, the ancient afterglow of the Big Bang, enabling scientists to tightly constrain the amount and distribution of dark matter across the universe. But that's just the beginning. Gravitational lensing, a fascinating cosmic phenomenon where light from distant galaxies bends around massive foreground objects, reveals the hidden scaffolding of dark matter in galaxies and clusters. Surveys like the Dark Energy Survey meticulously map these lensing effects, that painting a detailed picture of the invisible matter that shapes our universe. Each method of detection, though powerful, comes with its own set of challenges and uncertainties. Yet together, they form a robust, multi-pronged strategy to decode one of the universe's deepest mysteries. As technology leaps forward and new data pours in from cutting-edge observatories, these complex investigative techniques bring us ever closer to unraveling the nature of dark matter, an enigmatic substance that holds the cosmos together. But the quest doesn't stop there. Beyond dark matter lies an even more profound puzzle: dark energy. Making up about 70% of the universe's total energy content, dark energy drives the accelerated expansion of the universe, a discovery that shocked scientists in the late 1990s through observations of distant Type Ia supernovae. This finding shattered the old assumption that cosmic expansion should be slowing down due to gravity's pull. Instead, it revealed a mysterious force acting like anti-gravity, pushing galaxies apart and stretching the very fabric of space-time. What exactly is dark energy? Is it a property inherent to space itself, or is it a dynamic, unknown form of energy fluctuating over time and space? The cosmological constant, a term Einstein once introduced and later discarded as part of his general relativity equations, stands as one candidate: a uniform energy density permeating space. Alternatively, the idea of quintessence suggests a dynamic field. one that evolves and changes, a tantalizing possibility that keeps researchers on their toes. Despite the wealth of data collected from space telescopes, ground observatories, and the cosmic microwave background, dark energy remains frustratingly elusive. Its true essence continues to evade full understanding, pushing scientists to innovate new technologies and explore revolutionary theoretical frameworks. Dark energy's repulsive force counteracts gravity, accelerating the universe's expansion and reshaping our cosmic destiny. Imagine space itself as an inflating balloon. In the early universe, dark energy's effects were subtle, dwarfed by gravity's role in gathering matter into stars, galaxies, and vast cosmic structures. But as the balloon expands, dark energy takes center stage, stretching space at an ever-increasing pace. This acceleration means galaxies drift apart faster and faster, hinting at a chilling future. If dark energy continues unchecked, we may face the big freeze, where galaxies recede beyond each other's reach, stars burn out, and the universe fades into a cold, dark silence. Some theories even warn of a big rip, a cataclysmic scenario where dark energy's power grows so immense it tears apart galaxies, stars, and ultimately the atoms themselves. Understanding dark energy is thus more than an academic pursuit. It's a quest to foresee the ultimate fate of everything we know. Meanwhile, dark matter remains an equally captivating cosmic cornerstone. Unlike dark energy, dark matter doesn't interact with light. It neither emits nor absorbs it, making it invisible to telescopes. Its presence is betrayed only by its gravitational influence on visible matter and the large-scale structure of the universe. Thought to constitute roughly 27% of the universe's mass energy content, dark matter remains shrouded in mystery. Leading theories propose that dark matter is composed of weakly interacting massive particles, or WIMPs. These elusive particles barely interact with normal matter except through gravity, explaining their ghostly invisibility. Another intriguing candidate is the axion, an ultralight particle even harder to detect, interacting so faintly it slips through even the feeblest of forces. Beyond WIMPs and axions, other possibilities emerge. Sterile neutrinos, a form of neutrino that doesn't interact via standard forces, and primordial black holes formed in the universe's infancy, each offering exciting yet observationally challenging explanations. Together, these ideas form the front lines of a cosmic detective story, one that scientists are relentlessly pursuing to illuminate the dark side of our universe. While particle accelerators like the Large Hadron Collider and sophisticated underground detection experiments have yet to capture definitive proof of dark matter, their relentless efforts continue to sharpen our understanding and narrow the scope of possibilities. This ongoing pursuit embodies the essence of human curiosity and ingenuity, propelling advances in cutting-edge technology and inspiring revolutionary theoretical breakthroughs. The quest to unveil the true nature of dark matter is not merely about explaining the mysterious 27% of the universe's mass energy content. It also seeks to answer fundamental questions about the formation and evolution of cosmic structures, from the smallest galaxies to sprawling galaxy clusters. And then there's dark energy, the enigmatic force accelerating the expansion of the cosmos, raising profound and perplexing questions that challenge the very foundations of physics. Is dark energy a constant property of space itself, as suggested by Einstein's cosmological constant, or is it a dynamic, evolving force, shifting across time and space? While the cosmological constant posits a uniform, unchanging energy density, alternative theories like quintessence imagine dark energy as a mutable influence, its intensity waxing and waning as the universe unfolds. The mystery deepens when scientists ask why dark energy exists at all, and how it came to dominate the universe's expansion only in the relatively recent cosmic past. Could dark energy be connected to one of the known fundamental forces, or does it herald a completely new, undiscovered force shaping the cosmos? The ultimate fate of the universe hinges on these questions. Will the accelerated expansion continue forever, culminating in a cold, desolate, big freeze? Or might it escalate toward a catastrophic, big rip, tearing galaxies, stars, and even atomic particles apart? Answering these riddles demands not only daring leaps in theoretical physics, but also innovative observational techniques capable of capturing ever more precise data to illuminate the dark corners of the universe. Together, dark matter and dark energy present some of the most profound and tantalizing enigmas in modern science. They are thought to constitute roughly 95% of the universe's total mass energy, yet remain almost entirely invisible and unexplained within our current theoretical frameworks. Dark matter, for instance, exerts gravitational influence that sculpts the cosmic web, forming the invisible scaffolding for galaxies and large-scale structures. Yet it neither emits nor absorbs light, slipping through traditional detection methods like a ghost in the cosmic night. This invisibility hints at the possibility of a hidden, dark sector, a shadow world of particles and forces yet to be discovered, challenging physicists to rethink and expand the standard model of particle physics. Meanwhile, dark energy confronts our understanding of gravity and the universe's grandest scales. The concept of a repulsive force accelerating cosmic expansion was a startling addition to Einstein's general relativity, initially encapsulated by the cosmological constant. However, if dark energy proves to be dynamic rather than static, it may demand entirely new physics to explain its origin, nature, and destiny. This unfolding cosmic mystery is pushing the boundaries of cosmology into uncharted territory, promising to reshape our comprehension of the universe and the laws that govern it. It could imply the existence of entirely new fields or forces, mysterious, unseen players in the cosmic drama that have so far escaped detection. This tantalizing possibility has sparked intense speculation about the quintessence field and other exotic mechanisms, enigmatic forces that might be propelling the universe's accelerated expansion. The discovery of dark energy has rewritten our cosmic script, introducing profound questions about the ultimate fate of the universe itself. Could the cosmos end in a chilling big freeze, where all activity grinds to a halt, or a catastrophic big rip, tearing everything apart? These scenarios challenge our deepest assumptions about destiny on a universal scale. And so, these perplexing challenges drive physicists to forge new theoretical pathways, seeking to weave dark energy and dark matter into a grander, unified framework. Such breakthroughs could revolutionize our grasp of fundamental physics, opening doors to realms of knowledge once thought beyond reach. The expanding universe presents a vast frontier filled with mysteries that captivate the minds of cosmologists and astrophysicists alike. One of the most profound puzzles is the nature of this expansion, its origins, its behavior, and its destiny. While the Big Bang theory laid the foundation by predicting expansion, the startling revelation that this expansion is accelerating adds layers of complexity. This unexpected acceleration forces us to question whether Einstein's general relativity, our cornerstone theory of gravity, needs revisiting or even radical modification when applied on cosmic scales. Moreover, the universe's ultimate fate remains a subject of fervent debate. Will it culminate in a quiet, frozen abyss, collapse back onto itself in a fiery big crunch, or be torn asunder in a violent big rip? Each scenario carries profound implications for the fate of matter, energy, and even time itself. Another cosmic conundrum lies in the precise measurement of the Hubble constant, the parameter that quantifies the universe's expansion rate. Intriguingly, different methods of measurement yield conflicting results, a puzzle known as the Hubble tension. For example, values derived from the cosmic microwave background, the faint afterglow of the Big Bang, don't quite match those obtained from observing distant supernovae. Resolving this tension could unveil hidden errors in our measurements, or hint at groundbreaking new physics lurking beyond our current understanding. Beneath these questions lie even deeper mysteries. The very initial conditions that triggered the Big Bang, and the enigmatic nature of time and space at the universe's birth singularity. Was the universe born from a fragile quantum state, or is it but one bubble in a vast multiverse where countless other universes with different physical laws exist? These profound questions drive researchers to invent ever more sophisticated observational tools, from next-generation space telescopes to advanced gravitational wave detectors, while theoretical physics ventures boldly into uncharted realms. Through these relentless efforts, we stand poised not only to solve age-old cosmic riddles, but also to uncover new phenomena that could forever transform our understanding of the cosmos. The concept of the expanding universe rests on a foundation of compelling astrophysical evidence, each piece reinforcing the picture of a cosmos stretching and evolving over nearly 14 billion years. The earliest and most direct evidence comes from the redshift of light emitted by distant galaxies, a discovery made in the 1920s by American astronomer Edwin Hubble. With painstaking observations, Hubble demonstrated that galaxies are moving away from us at speeds proportional to their distance, a relationship now immortalized as Hubble's law. This redshift occurs because the light waves from these receding galaxies stretch out, shifting toward the red end of the spectrum, much like the descending pitch of an ambulance siren fading into the distance. This simple yet profound observation remains a cornerstone of modern cosmology, a beacon illuminating the dynamic, ever-changing nature of our universe. Another compelling piece of evidence lies in the cosmic microwave background radiation, known simply as the CMB. This faint, almost ethereal glow fills every corner of the universe, acting as the afterglow of the Big Bang itself. Discovered by Arno Penzias and Robert Wilson in 1965, the CMB offers us an extraordinary snapshot of the infant cosmos, revealing conditions from roughly 380,000 years after the universe's fiery birth. Its remarkable uniformity, punctuated by subtle fluctuations, supports the idea that the universe has been expanding and cooling ever since that primordial moment. And the story doesn't end there. Detailed observations of the vast cosmic web, the sprawling distribution of galaxies and galaxy clusters, align perfectly with predictions made by the theory of an expanding universe. These enormous structures emerge from the gravitational dance of matter, gradually assembling through hierarchical clustering on an ever-expanding cosmic stage. Further evidence comes from the brilliant explosions of stars known as supernovae, particularly the Type 1a variety. These stellar events act as cosmic lighthouses, or standard candles, because of their consistent brightness. In the late 1990s, two independent research teams made a stunning discovery. These supernovae appeared dimmer than expected, suggesting they were farther away than their redshift measurements alone indicated. This revelation wasn't just about expansion. It hinted at an accelerated expansion of the universe, introducing the mysterious force we now call dark energy. Each of these discoveries weaves into a compelling narrative of a dynamic, ever-expanding cosmos, one that constantly stretches the boundaries of our understanding and ignites our curiosity about its origins, evolution, and ultimate fate. Redshift plays a central role in this cosmic tale. Fundamentally, redshift describes how light from distant objects, like galaxies, is stretched toward longer, redder wavelengths as those objects speed away from us. This phenomenon was first systematically observed by Edwin Hubble in the 1920s. His groundbreaking work led to Hubble's law, revealing that the farther a galaxy lies, the faster it recedes. This relationship shattered the long-held view of a static universe and firmly established the reality of cosmic expansion, providing critical support for the Big Bang theory, the idea that the universe began in a hot, dense state and has been expanding ever since. Beyond its conceptual importance, redshift is a practical tool astronomers rely on to map the cosmos. By measuring the redshift of galaxies, scientists determine how fast they're moving away from us, which, when combined with other distance measurements, allows them to chart the large-scale structure of the universe and track how it changes over time. Analyzing the spectral lines of light also reveals invaluable information about the composition, motion, and environment of distant celestial bodies. More intriguingly, redshift enables us to peer into the deep past. Light from the most distant galaxies has traveled billions of years to reach us, effectively allowing astronomers to look back in time and study the universe in its earliest stages. Through this cosmic time machine, researchers investigate galaxy formation, the elusive behavior of dark matter, and the role of dark energy in accelerating cosmic expansion. So, redshift is far more than just a measure of distance or velocity. It is a window into the ancient universe, a fundamental key to unlocking the mysteries of cosmology, and a vital instrument in our quest to comprehend the vast, expanding, and endlessly mysterious cosmos we call home. And so begins the grand cosmic saga, the expansion of the universe, a force that sculpts the very fabric of existence on scales both vast and minute. From the sprawling clusters of galaxies to the seemingly empty cosmic voids, this relentless stretching of space influences everything in its path, shaping the evolution of stars, galaxies, and the colossal architecture of the cosmos itself. In the infancy of the universe, matter was a near-uniform sea, an almost featureless expanse. But hidden within this smoothness were tiny quantum ripples, fluctuations in density that, over billions of years, gravity amplified into a magnificent cosmic web. This intricate network of galaxies and dark matter filaments forms the backbone of the universe's large-scale structure, the very framework upon which galaxies and clusters assemble. Galaxy clusters, titans of gravitational binding, continue to grow by drawing in material from their surroundings. Though the universe expands, these clusters cling together tightly, while the space between them stretches ever wider, causing them to drift apart in the grand cosmic ballet. The vast, empty cosmic voids between clusters grow, barren and dark, vast expanses where few galaxies dare to tread. One of the most striking signatures of this expansion is the redshift, the stretching of light waves from distant objects, shifting them toward longer, redder wavelengths. This cosmic Doppler effect not only reveals the universe's expansion rate, but also colors our observations, altering spectral lines and complicating the interpretation of astrophysical data. Zooming in, the universe's expansion subtly influences the life cycles of galaxies and stars. As space expands, the gas that fuels star formation, mostly hydrogen and helium, becomes increasingly diffuse, thinning out the raw materials needed to birth new stars. Galaxies evolve under this slow starvation, their growth throttled by the spreading cosmos. Meanwhile, the residual heat from the Big Bang, the cosmic microwave background radiation, cools as the universe stretches. This gradual temperature drop marks a changing thermal history, affecting how galaxies form and how gases behave in the vast spaces between stars. Together, these processes weave a complex, interconnected cosmic tapestry. The expansion drives the growth of large-scale structures, shapes dynamics within and between galaxy clusters, and orchestrates the birth and death of stars and galaxies. Unlocking the secrets of this vast cosmic dance demands cutting-edge observations and the most advanced simulations, pushing the frontiers of astronomy, cosmology, and physics. Looking far ahead, the ultimate destiny of the universe hangs in the balance, shrouded in mystery and speculation. The Big Freeze, or heat death, is a leading theory, painting a chilling vision of endless expansion. As dark energy propels galaxies apart, star formation slows to a trickle, gas thins out, and existing stars burn away into cold remnants, white dwarfs, neutron stars, and black holes, until even they fade, leaving a cold, dark, lifeless cosmos approaching absolute zero. Yet another possibility looms, the Big Crunch. If dark energy wanes or reverses, gravity might seize control, halting and then reversing the expansion. The cosmos could contract back upon itself in a dramatic collapse, ending the story in a fiery finale. In the ever-expanding mystery of our universe, every revelation sparks new questions. The story of cosmic expansion is far from complete, a profound journey that continues to unfold across the vastness of space and time. And the universe might one day reach a critical tipping point, a cosmic moment when the combined gravitational pull of all its mass becomes so immense that it reverses the grand expansion. In this scenario, galaxies, stars, and eventually every particle of matter would be drawn inward, collapsing into an unimaginably hot and dense state, reminiscent of the Big Bang itself. This dramatic cycle of expansion and contraction paints a picture of a universe that endlessly breathes, expanding outwards and then folding back upon itself like a cosmic heartbeat. Yet, this captivating cycle is only one of several potential destinies. Dark energy, an enigmatic force accelerating the universe's expansion, complicates this vision. If dark energy's mysterious repulsive power continues to grow stronger, it could drive the cosmos toward a far more violent fate known as the Big Rip. Imagine the universe stretched to its breaking point, where galaxy clusters are torn apart first, followed by individual galaxies, stars, and planets. Ultimately, the very atoms holding matter together would unravel, dissolving everything into fundamental particles scattered across an expanding void. This harrowing end would leave the universe a desolate and fragmented place, unrecognizable from the structured cosmos we know. Beyond these cosmic finales, some theories reach even further, invoking the strange and subtle laws of quantum mechanics. Concepts such as quantum fluctuations and the multiverse hint at realities where our universe might spawn countless baby universes through sudden phase transitions or tunneling events. These ideas stretch the boundaries of human understanding, challenging our notions of space, time, and existence itself. They propose that what we see might be just one bubble in an infinite cosmic sea, forever changing, forever birthing new realms. The path to unraveling the universe's ultimate fate depends heavily on our grasp of dark energy, the curvature of space, and the intricate dance of fundamental particles and forces. Future observations, whether from powerful telescopes or revolutionary experiments, alongside advances in theoretical physics, will be our guiding light, illuminating the profound mysteries of the cosmos. Meanwhile, within this vast universe, another frontier beckons: the search for exoplanets. These distant worlds orbit stars far beyond our sun, presenting an astonishing diversity of environments. Some resemble Earth, hinting at the possibility of life, while others boast bizarre atmospheres and alien weather systems that challenge every expectation. The discovery of exoplanets has revolutionized our cosmic perspective, revealing that planets are far from rare. They are abundant and varied across the galaxy. The journey began in 1992 with the detection of the first confirmed exoplanet orbiting a pulsar, a dense neutron star in the constellation Virgo. Since then, technological leaps have unveiled more than 4,000 of these distant worlds, each offering clues to the processes that shape planetary systems. Astronomers use ingenious techniques to find these elusive planets, chief among them the transit method, watching for tiny dips in starlight as a planet crosses in front of its star, revealing its size and atmospheric composition. Another technique, the radial velocity method, tracks the subtle wobble of stars caused by the gravitational tug of orbiting planets, exposing the hidden companions that masses and orbits. Together, these methods have transformed our understanding of the cosmos, unveiling a mesmerizing cosmic dance of planets and stars beyond our solar system. Yet many exoplanets defy expectations, following strange orbits and displaying puzzling behaviors that continue to challenge astronomers and inspire new questions about the formation and evolution of planetary systems. In the end, the story of the universe, from its grand cosmic fate to the smallest distant worlds, remains one of wonder, discovery, and infinite possibility. And yet, the universe continues to surprise us. In distant solar systems scattered across the Milky Way, astronomers have found exoplanets that defy the logic shaped by our own cosmic neighborhood. Unlike the nearly circular orbits of Earth and its planetary siblings, many of these alien worlds trace out extreme elliptical paths or follow orbits tilted at dramatic inclinations. These erratic trajectories suggest a past filled with chaos, perhaps gravitational tugs from unseen planets, or even close encounters with wandering stars that disrupted the delicate order of their home systems. Some of these exoplanets are so perilously close to their stars that they complete a full orbit in just a few days. These tight embraces lead to immense tidal forces, distorting their very structures and stripping away atmospheres in ways that we are only beginning to grasp. In some cases, those same atmospheres reveal strange, almost alchemical signatures: titanium oxide, vanadium oxide, compounds rarely seen in such contexts. These exotic molecules cause temperature inversions, upending our expectations of how heat flows and weather unfolds on these planets. Even the skies of these worlds can appear utterly alien. Observations hint at clouds made not of water vapor, but of silicates, yes, rock, and grains akin to sand, suspended in scorching upper atmospheres. Weather on these planets may resemble something out of science fiction: glass rains, winds that tear at thousands of kilometers per hour, and skies that glow with unfamiliar hues. Such anomalies have turned these distant planets into laboratories of the strange, urging scientists to revisit long-held assumptions. And nowhere is this more evident than in the diversity of the exoplanets themselves. Take hot Jupiters, for instance. These are massive gas giants found unexpectedly close to their stars, a position that contradicts prevailing models of planetary formation. According to conventional wisdom, such giants should have formed much farther out, where cool temperatures allowed gas to accumulate. And yet, here they are, roasting in stellar heat. How did they migrate inward without being destroyed? What kept their atmospheres intact during the journey? Each answer births new questions, opening a window into the mechanisms that sculpt planetary systems. Then come the terrestrial planets, rocky, Earth-like bodies, especially those nestled within their stars' habitable zones, the coveted regions where liquid water might persist. Yet proximity to this so-called Goldilocks zone tells us little about true habitability. A thick atmosphere loaded with carbon dioxide could turn a promising world into a hellish greenhouse, while a tenuous one might offer no shield from cosmic radiation. Some may harbor volcanic plains under sulfurous skies, others might be locked in tidal grips, showing only one face to their sun. Perhaps most enigmatic of all are the super-Earths. These rocky planets, larger than our own, are among the most frequently discovered, but their geology, tectonics, and atmospheric chemistry remain largely unknown. Could they support life? Do they have magnetic fields? Oceans? Theories abound, but firm answers remain elusive. And in the heart of this mystery sits the habitable zone, not a guarantee of life, but a compass pointing to possibility. This narrow belt around a star represents the delicate balance between freezing cold and searing heat. Yet, a planet's ability to sustain life depends on far more than its orbit. Atmosphere, magnetism, internal heat, and even neighboring celestial bodies all play crucial roles. A habitable zone is a starting point, not a verdict, a place to ask the right questions. This pursuit of the alien and the familiar alike found a powerful ally in the Kepler Space Telescope. Launched in 2009, Kepler set its gaze on a small swath of the Milky Way and in doing so, reshaped our understanding of the galaxy. By the end of its mission, it had confirmed over 2,600 exoplanets, with thousands more awaiting verification. These discoveries exposed a universe teeming with worlds, perhaps billions of them. Kepler revealed that our solar system is not the template, but one of many variations. It found planets smaller than Earth, gas giants larger than Jupiter, and systems where planets pack tightly around their stars or orbit in chaotic elegance. Among these are Earth-sized planets in habitable zones, tantalizing possibilities for life beyond. With every new planet discovered, Kepler rewrote what we thought we knew about how worlds are born and how they evolve. Its legacy is not just a catalog of distant spheres, but a humbling reminder. The universe is more inventive, more diverse, and more mysterious than we ever imagined. But it has also deepened our understanding of the intricate forces that shape not just planets, but entire planetary systems, offering profound insights into how life might arise elsewhere in the cosmos. Across the vast expanse of our galaxy, thousands of exoplanets have been discovered, each a distant world orbiting a far-off star. Among them, a few stand out as especially tantalizing, planets that seem to hover at the intersection of scientific curiosity and the possibility of life. One such world is Kepler 1a6f. Nestled in the constellation Cygnus, some 500 light-years from Earth, this Earth-sized planet orbits a dim, cool red dwarf. What makes Kepler 186f extraordinary isn't just its size, but its location within the habitable zone of its star, the so-called Goldilocks zone, where temperatures might allow for liquid water. While we don't yet know what kind of atmosphere, if any, it possesses, its promise lies in its potential. A world not too hot, not too cold, but possibly just right. Then there's TRAPPIST-1e, a jewel among 7 Earth-sized planets encircling a faint star in the constellation Aquarius, just 40 light-years away. 3 of those planets sit comfortably in the habitable zone. But TRAPPIST-1e is particularly striking. With a mass and density similar to Earth's, it could very well have a rocky surface and a temperate climate. Its proximity to our solar system makes it one of the most accessible targets for upcoming telescopes, which may soon unveil its atmospheric secrets. And even closer, merely 2 light-years away, lies Proxima Centauri b, circling the star closest to our own. This planet also orbits within its star's habitable zone, making it a compelling candidate for further study. However, its parent star is prone to violent solar flares, casting doubt on the planet's ability to retain a stable, life-supporting atmosphere. Even so, its nearness makes it an irresistible subject of interest. Other notable contenders include Ross 128b and LHS 1140b, worlds that, like their better-known cousins, hover on the edge of possibility. Each one could hold answers to one of humanity's most enduring questions. Are we alone? Yet for all their promise, the search for life beyond Earth is fraught with challenges. The sheer scale of space renders interstellar travel a distant dream. Even the nearest of these worlds are separated from us by unimaginable distances, far beyond the reach of current spacecraft. Instead, astronomers must rely on the subtle language of light. By analyzing the spectral fingerprints left in starlight passing through a planet's atmosphere, they can begin to infer its chemical makeup. But these signals are faint, easily overwhelmed by the glare of their parent stars. Decoding them demands extraordinary precision and ever-advancing technology. Then comes the matter of interpretation. Not all signs of life are clear-cut. Oxygen, for example, is considered a powerful biosignature on Earth due to its abundance from photosynthesis, but it can also arise through non-biological means, such as the photolysis of water under ultraviolet light. To determine whether oxygen or any other chemical marker is truly a product of life, scientists must understand a planet's full environmental context, its geologic history, its climate systems, and the interplay of its chemistry. The road ahead is daunting, filled with technical and conceptual hurdles, but it is also one of the most exhilarating frontiers in modern science. As our tools sharpen and our gaze extends further into the galaxy, we may be on the cusp of answering a question that has echoed through the ages. Is there life beyond Earth? Moreover, life beyond Earth might not merely resemble what we know. It could be entirely alien, shaped by chemistries and biological processes yet unimagined by modern science. This opens a startling possibility that extraterrestrial life may already be out there, undetected or misclassified, simply because it doesn't align with our Earth-centric expectations. The search for life then becomes more than a scientific mission. It is a test of our imagination, our technology, and our ability to interpret the unfamiliar. This cosmic pursuit unfolds against the backdrop of mysteries that begin with our own solar system. How exactly did it come to be? The prevailing theory, the nebular hypothesis, suggests that 4.6 billion years ago, a vast cloud of gas and dust collapsed under gravity, igniting the sun and giving rise to the planets. Yet this story remains riddled with unanswered questions. What determined the strange and stunning diversity among the planets, from rocky Earth to colossal Jupiter and distant, icy Neptune? Scientists suspect that gravitational forces, collisions, and accretion played pivotal roles, but the precise mechanics are still being deciphered. Among the more puzzling chapters in this tale is the Late Heavy Bombardment, a period nearly 700 million years after the solar system's birth, marked by a violent barrage of impacts on the inner planets. What caused this sudden spike in collisions? Some astronomers theorize that the migration of giant planets like Jupiter and Saturn destabilized the orbits of countless smaller bodies, hurling them inward from the asteroid and Kuiper belts. These cosmic collisions may have sown the seeds of life on Earth, delivering water and organic compounds essential for biology. Yet this remains largely speculative, built on clues from crater counts and ancient planetary scars. The enigma deepens as we turn to the Sun, the engine of our solar system. Its origin lies within a stellar nursery, where a dense knot of gas collapsed, possibly nudged by a nearby supernova. As it spun, it flattened into a disk with a newborn protostar at the center. Eventually, nuclear fusion ignited, giving birth to our star. The leftover debris in that disk coalesced into planets, moons, and more. Still, the Sun harbors secrets. Chief among them, why is its corona, the outer atmosphere, inexplicably hotter than the surface below? Reaching temperatures over 1,000,000 degrees Celsius, the corona defies logic, driving scientists to investigate phenomena like magnetic reconnection and plasma waves. Then there's the solar magnetic cycle, a roughly 11-year rhythm during which the sun's magnetic field flips, sparking fluctuations in solar activity, sunspots, flares, and ejections that ripple across space and affect Earth. Despite its predictability, the forces steering this cycle and its variability remain elusive. Understanding these stellar dynamics is more than academic. It holds the key to predicting solar storms that could one day impact our technological civilization. In every layer of this exploration, from alien biology to the molten heart of our sun, lies a profound truth. The universe does not yield its secrets easily. But with every mission, every telescope, and every question we dare to ask, we edge closer to understanding the deep and ancient story written in the stars, but also provides critical insights into the behavior of other stars across the cosmos. The planets within our solar system are more than just celestial bodies orbiting the sun. They are treasure troves of mystery, each presenting a dazzling array of unexplained phenomena that continue to captivate scientists and drive relentless research. Take Jupiter's Great Red Spot, for example, a colossal storm larger than the entire Earth that has roared for at least 400 years. Despite its astonishing longevity, the secrets behind its persistence and its slow, puzzling shrinkage in recent decades remain elusive. This storm's incredible stability defies everything we understand about atmospheric dynamics on Earth, pushing scientists to explore Jupiter's unique atmospheric chemistry and the mysterious internal heat sources that may be fueling this cosmic tempest. Another bewildering enigma lies at Saturn's North Pole, the mesmerizing hexagon. First discovered by the Voyager spacecraft in the early 1980s, and later examined in exquisite detail by the Cassini mission, this six-sided jet stream stretches over 20,000 miles and exhibits a baffling stability. Hexagonal patterns are rare in nature, but to find one swirling with such precision amid Saturn's turbulent atmosphere is downright perplexing. Scientists hypothesize that this phenomenon results from complex interactions between deep atmospheric currents and Saturn's rapid rotation, yet no model has fully unraveled the hexagon's secrets. Mars, our enigmatic red neighbor, adds its own share of mysteries. Among the most intriguing are the recurring slope lineae, dark streaks that appear seasonally on Martian slopes. These streaks have sparked debate, with some scientists suggesting they are evidence of flowing briny water, while others argue for dry granular flows or melting subsurface ice under precise conditions. Each hypothesis complicates our understanding of Martian hydrology and the tantalizing question of whether life could exist or once existed on the red planet. Even the dwarf planets, those smaller and more distant members of our solar family, hold astonishing surprises. Pluto, once considered merely a distant, frozen rock, was revealed by the New Horizons spacecraft in 2015 to be a vibrant, geologically active world. Its surface boasts vast nitrogen ice plains, towering mountains of water ice, and possible cryovolcanoes, volcanoes that erupt icy materials rather than molten rock. One of the most captivating features is Sputnik Planitia, a heart-shaped basin that appears remarkably young, hinting at ongoing geological processes. Floating icebergs and convection currents within this basin defy the expectation that small, far-flung worlds are geologically dead. Closer to home, Ceres, the largest object in the asteroid belt and the only dwarf planet within the inner solar system, holds its own intriguing puzzles. The Dawn spacecraft revealed bright spots primarily in the Achater crater, which are deposits of sodium carbonate, a type of salt. These spots suggest that subsurface briny water once existed on Ceres, raising profound questions about its potential to support life. Adding another layer of mystery, Dawn also detected organic molecules on Ceres, sparking questions about their origin and how they arrived there. Could these molecules have formed on Ceres itself, or were they delivered through cosmic processes we have yet to fully understand? These enigmatic phenomena, on planets and dwarf worlds alike, remind us that our solar system is a vast, dynamic laboratory filled with diversity and complexity. They challenge our understanding, fuel our curiosity, and drive humanity's unending quest to uncover the secrets of our cosmic neighborhood. In studying these celestial wonders, we not only learn about planetary formation and evolution, but also ignite hope that life might exist, or have once existed, in the most unexpected corners of the universe. Asteroids and comets stand as cosmic time capsules, guarding precious secrets from the dawn of our solar system. These small, ancient travelers are remnants of a chaotic era more than 4.6 billion years ago, holding pristine material untouched by the forces that reshaped larger planets and moons. By studying them, scientists peer back in time when the sun and planets were just beginning to emerge from a swirling cloud of gas and dust. Asteroids, mostly found in the vast belt between Mars and Jupiter, reveal the raw ingredients that built the rocky worlds like Earth. Their varied compositions reflect the diverse materials scattered across the early solar nebula. Among these, carbon-rich asteroids harbor organic compounds and water-bearing minerals, hinting at their crucial role in delivering the essential elements for life to our young planet. Through collisions and fragmentations, these rocky bodies tell a story of violent interactions that shaped the architecture of our planetary neighborhood. Comets, in stark contrast, hail from the distant, frozen outskirts of the solar system, the Oort cloud and Kuiper belt. These icy wanderers carry volatile compounds like water, carbon dioxide, methane, and ammonia, preserving a chemical snapshot of the early solar nebula's coldest regions. Missions like the European Space Agency's Rosetta, which closely studied Comet 67P/Churyumov-Gerasimenko, uncovered complex organic molecules, raising tantalizing possibilities about comets delivering the building blocks of life to Earth. Isotopic analyses of cometary water compared to Earth's oceans further illuminate the cosmic origins of our planet's precious water. Together, the revelations from asteroids and comets weave a vivid tapestry of the solar system's infancy. Each discovery helps scientists reconstruct the sequence of events that forged the planets and shaped the intricate, diverse system we observe today. Beyond our solar system, space exploration has revolutionized our view of the cosmos itself. The Hubble Space Telescope, a monumental sentinel in Earth's orbit, has unveiled breathtaking vistas of the universe. It has revealed thousands of galaxies, some formed mere hundreds of millions of years after the Big Bang, offering a window into the universe's turbulent youth. Hubble's observations also led to the astonishing discovery of dark energy, a mysterious force accelerating the universe's expansion, fundamentally altering our understanding of cosmic destiny. Closer to home, Mars missions like the rovers Curiosity and Perseverance have peeled back the red planet's dusty veil. Evidence of ancient water flows and complex geology suggests Mars once harbored conditions that might have supported microbial life, igniting fresh hope in the quest for life beyond Earth. Meanwhile, the Cassini-Huygens mission to Saturn revealed wonders within the gas giant's realm. Diving through icy plumes erupting from Enceladus, one of Saturn's moons, Cassini detected complex organic molecules and a hidden subsurface ocean, a promising sign that this frozen world could sustain life. Human space exploration etched its own legacy through the Apollo missions, which achieved humanity's first footprints on the moon. The lunar rocks brought back have provided an invaluable archive of the moon's composition and history, shedding light on its relationship with Earth and the broader cosmic environment. These samples have deepened our understanding of solar-wind interactions and the ancient impacts that have shaped the lunar surface. In unraveling these cosmic stories, from the tiniest asteroids to distant galaxies, humanity continues to uncover the profound mysteries of our origins and place in the universe. Lastly, the Voyager probes launched in the 1970s continue their incredible journey through interstellar space, sending back invaluable data that offer humanity its first direct glimpse into this uncharted cosmic frontier. Each mission, whether robotic or manned, has played a pivotal role in transforming our understanding of the universe. They have unraveled mysteries that challenge long-held scientific paradigms and ignite the imagination of generations eager to explore the final frontier. Past space missions have delivered a treasure trove of knowledge, yet they have also opened new doors to profound unknowns, enigmas that continue to puzzle scientists and fuel the relentless drive for future exploration. Among these mysteries are the puzzling findings from the Apollo missions to the moon. The rock samples they returned were rich with clues, but also riddled with questions. For example, the moon's unexpectedly high levels of isotopes like oxygen-17 and oxygen-18 closely mirror those found on Earth, suggesting a shared origin or a cataclysmic event in our planetary past. The prevailing giant impact hypothesis, which posits that the moon from debris after a colossal collision between the early Earth and a Mars-sized body, remains compelling but incomplete. Key details about the exact mechanics and aftermath of this cosmic smash-up still elude researchers. The Viking missions to Mars in the 1970s, designed to detect signs of life, sparked intense debate. While most results were interpreted as negative, the labeled release experiment produced ambiguous data that some scientists argue could be consistent with microbial metabolism. This ambiguity has kept the question of Martian life tantalizingly open and underscores the need for more advanced life detection technologies on future missions. Jupiter's system, illuminated by the Galileo spacecraft, revealed spectacular phenomena, especially concerning Europa. Galileo's evidence of a vast subsurface ocean beneath Europa's icy shell positions this moon as one of the most promising locations to search for extraterrestrial life. Yet, critical questions about the ice's thickness, ocean composition, and potential hydrothermal activity remain unanswered, as Galileo was not equipped to probe these depths with precision. Returning to Saturn. To Saturn, the Cassini mission offered breathtaking insights before its dramatic finale, plunging into Saturn's atmosphere to protect its moons from contamination. Cassini's study of Saturn and its moons, especially the discovery of geysers erupting from Enceladus' south pole, has been groundbreaking. However, many mysteries linger. The intricate internal structure of Saturn, the precise makeup of its rings, and the driving forces behind the geological activity on its moons all remain elusive. Each mission has broadened our cosmic horizons while simultaneously sparking new questions, ensuring that our quest to understand the solar system remains a thrilling and ongoing journey. Meanwhile, the Hubble Space Telescope has stood as a monumental pillar in modern astronomy. Its discoveries have reshaped our view of the cosmos, none more striking than the revelation of the universe's accelerating expansion. This phenomenon, attributed to the enigmatic force known as dark energy, was unveiled through meticulous observations of distant supernovae, stellar explosions that illuminate the fabric of space-time itself. Hubble revealed a universe far stranger than anyone had imagined. It showed us not only that the cosmos is expanding, but that this expansion is accelerating, a discovery that sent shockwaves through the scientific community. This accelerating growth points to a mysterious force, now known as dark energy, pushing galaxies apart with an invisible hand. Despite countless theories, dark energy remains one of the deepest puzzles in modern cosmology, challenging our fundamental grasp of the universe's architecture and its ultimate destiny. And yet, Hubble's revelations didn't stop there. It opened our eyes to the bewildering diversity of exoplanets, worlds orbiting stars beyond our solar system. By analyzing the faint light filtering through alien atmospheres, the telescope detected surprising chemicals, water vapor, methane, and even subtle hints that could be signs of life. These findings complicate what we thought we knew about where life might thrive, revealing an astonishing variety of planetary atmospheres and climates. Take K2-18b, a super-Earth nestled in its star's habitable zone. Water vapor in its skies ignites tantalizing questions about life and the complex geochemistry shaping these distant worlds. Hubble also peered deep into galaxies, uncovering chaotic centers dominated by supermassive black holes and star clusters forming under extreme conditions. Its iconic deep field images expose galaxies from more than 13 billion years ago, cosmic infants in a tumultuous youth, smaller and more irregular than today's majestic spirals and ellipticals. These glimpses into the early universe raise profound questions. How did these cosmic building blocks evolve into the galaxies we see now? What forces sculpted the grand designs of stars and gas? Closer to home, Hubble has captured the dynamic weather of our solar system's giants. Saturn's seasonal shifts and Jupiter's ever-changing storms, including the famous Great Red Spot, come alive in unprecedented detail. These observations reveal just how complex and volatile planetary atmospheres can be, even on worlds we know intimately. All these discoveries have not only broadened our cosmic understanding, but also paved the way for future exploration. The baton now passes to the James Webb Space Telescope and other next-generation instruments poised to delve deeper into these enduring mysteries. Yet as humanity sets its sights on the stars, new unknowns loom large. The effects of long-term space travel on the human body are a frontier still fraught with uncertainty. Microgravity causes muscle and bone loss, but the silent threat of cosmic radiation outside Earth's protective magnetosphere poses grave risks, including heightened cancer danger during prolonged missions, like a potential Mars voyage lasting years. Developing effective shielding against this invisible hazard is a race against time. Beyond human health, the sustainability of life far from Earth is a monumental challenge. Growing food, recycling water, and producing oxygen aboard spacecraft or habitats demand breakthroughs. Experiments aboard the International Space Station prove plants can grow in microgravity, but scaling this up to support a crew indefinitely remains largely theoretical. Alongside these biological hurdles, logistical obstacles and the need for autonomous systems capable of making life-critical decisions complicate the mission. The path to becoming an interplanetary species demands more than just technology. It calls for a profound deepening of our knowledge about living in the harsh vacuum of space. As we confront these cosmic mysteries and earthly challenges alike, the story of human exploration continues, a testament to our relentless curiosity and boundless ambition. And so, high above our planet, the International Space Station, ISS, orbits Earth at roughly 250 miles altitude, serving as an extraordinary observatory and scientific laboratory. This remarkable outpost offers a vantage point unlike any other, where astronauts conduct groundbreaking experiments impossible to replicate on Earth due to gravity's constraints. Within this microgravity environment, the ISS unlocks profound insights into the mysteries of the cosmos. Among its many instruments, the Alpha Magnetic Spectrometer 2, AMS-02, stands out as a marvel of particle physics. Mounted on the ISS, AMS-02 detects cosmic rays with unparalleled sensitivity, capturing billions of these high-energy particles as they bombard our solar system. This treasure trove of data holds the potential to unravel the enigmatic nature of dark matter, the elusive substance that makes up approximately 85% of the universe's mass, yet remains invisible and intangible to our instruments on Earth. Beyond particle physics, the ISS serves as a vital laboratory for studying the behavior of fluids, gases, and materials in microgravity. These investigations refine our understanding of stellar formation processes and the complex dynamics of interstellar matter, shedding light on the birth and evolution of galaxies and stars. The station also acts as a testbed for cutting-edge astrophysics and planetary science instruments. Take, for example, the Neutron Star Interior Composition Explorer, NICER, launched to the ISS in 2017. This specialized telescope peers into the cosmos using X-ray emissions to study neutron stars, black holes, and other extreme phenomena. Free from Earth's atmospheric distortions, NICER has provided unprecedented data about the dense matter inside neutron stars, revealing secrets about some of the universe's most extreme and mysterious environments. Thus, the ISS stands as a cornerstone in humanity's quest to decode the universe's deepest secrets, blending diverse scientific endeavors in a single orbiting laboratory. Quantum mechanics, the foundation of modern physics, plunges us into a realm both baffling and wondrous. It challenges our everyday notions of reality by revealing phenomena that defy classical intuition. At its core lies the mystery of superposition, where particles such as electrons exist in multiple states simultaneously, both here and there, until measured or observed. This idea is famously illustrated by Schrödinger's cat, a thought experiment where a cat trapped in a sealed box is simultaneously alive and dead until the box is opened. Superposition challenges the classical concepts of definite position and momentum, forcing us to reconsider the very fabric of reality. Entanglement is yet another quantum enigma. When two particles become entangled, the state of one instantly influences the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance because it implies faster-than-light information exchange, seemingly defying the theory of relativity. Countless experiments have confirmed entanglement's reality, paving the way for revolutionary technologies such as quantum computing and cryptography. These quantum machines promise to solve problems in seconds that would take classical computers thousands of years, potentially transforming medicine, climate science, and beyond. Moreover, quantum mechanics introduces particle-wave duality, the paradox that particles exhibit both wave-like and particle-like behaviors. The double-slit experiment perfectly demonstrates this, showing how photons create interference patterns when unobserved, but behave as discrete particles when measured. Such discoveries force us to accept a universe fundamentally governed by probability rather than certainty, an elegant yet perplexing cosmic dance beyond deterministic rules. In the grand tapestry of scientific discovery, from the orbiting laboratory of the ISS to the strange and beautiful laws of quantum mechanics, we stand at the frontier of understanding a universe that continues to inspire awe and wonder. And yet, these mysteries do more than illuminate the microscopic, they unravel our very sense of reality. In the quiet mathematical corridors of quantum mechanics, the universe sheds its classical skin and emerges in a form as enigmatic as it is revelatory. This isn't just physics, it's a philosophical upheaval. Quantum mechanics introduces a radical proposition. The cosmos is not a clockwork of certainty, but a realm laced with probability. Unlike Newton's world, where a particle's future can be determined from its present, quantum theory deals in likelihoods. Where might an electron be? What spin might it have? These questions have no definitive answers, only probabilities. This inherent randomness is not due to ignorance or incomplete data. It is built into the structure of the universe itself. It is, perhaps, the universe's most whispered secret. Determinism is an illusion. But the strangeness does not end there. Consider entanglement, a phenomenon that defies locality and bends the mind. Two particles, born together or otherwise linked, can influence one another across vast cosmic distances. Measure one and the other responds instantly. Einstein, uneasy with this, dubbed it spooky action at a distance. It appears to mock the speed limit set by light, and it dares us to rethink space and time, not as immutable arenas, but as pliable, intertwined tapestries. In this context, entanglement is not just a curiosity. It's a potential key to the ultimate unification of physics, a bridge between the smooth curvature of general relativity and the jittery dance of the quantum realm. Wave-particle duality furthers this erosion of classical boundaries. In a quantum world, entities like photons and electrons are not simply particles or waves. They are both, and neither, depending on how we look. The famed double-slit experiment illustrates this paradox with eerie clarity. Light and matter create interference patterns when unobserved, yet snap into discrete particles when watched. This suggests that observation itself alters the outcome. It invites an unsettling question. Does reality exist independently, or does our attention summon it into being? Thus, quantum mechanics dismantles the scaffoldings of classical thought and opens a portal to a cosmos governed by principles that verge on the surreal. And in a parallel but equally astonishing journey, relativity rewrites the grand architecture of space and time. Einstein's special relativity shatters the notion of universal time. When an object nears light speed, time does not flow evenly. It dilates. This isn't speculation. Atomic clocks on speeding jets have ticked more slowly than their grounded twins, confirming that time bends to velocity. The implication is profound. Time is not a river flowing uniformly for all, but a stream that twists and curls depending on how you move. General relativity expands this view, reframing gravity itself. No longer a force pulling at a distance, gravity becomes the curvature of space and time. Massive objects press into the fabric of the cosmos, distorting it, guiding the paths of other bodies not with invisible tethers but with warps in the very gridwork of existence. We do not orbit the sun because it pulls us, but because it has dented the cosmic floor beneath our feet. These revelations, quantum unpredictability, entangled unity, relativistic time, and the pliable contours of space, do more than challenge our understanding. They transform it. Together, they form a mosaic of a universe far stranger and more wondrous than ever imagined, where mystery is not a sign of ignorance, but a doorway to deeper truths. What we perceive as gravity is far more than a simple force pulling objects toward each other. It is a profound distortion of the very fabric of space and time. Among its most astonishing consequences lies the existence of black holes, enigmatic regions where the curvature of space-time becomes so extreme that nothing, not even light, can escape their grasp. Deep within a black hole, at a point known as the singularity, our current understanding of physics collapses. Here, mass is thought to become infinitely dense, and the familiar rules governing time and space break down, presenting one of the greatest challenges in modern science: how to reconcile Einstein's general relativity with the principles of quantum mechanics. General relativity also predicts the existence of gravitational waves, ripples in space-time generated by accelerating massive objects like colliding black holes or neutron stars. These waves, only confirmed experimentally in 2015 by the LIGO Observatory, have opened an unprecedented window into the cosmos. For the first time, scientists can listen to the universe, detecting cataclysmic events that were once the realm of theory alone. This breakthrough has revolutionized astrophysics, revealing the hidden dynamics of black hole mergers and other cosmic phenomena. Moreover, general relativity reshapes our understanding of the universe on the grandest scale. Observations of distant galaxies reveal that they are moving away from us, a discovery that points to the universe itself expanding. When traced backward, this expansion leads to the Big Bang theory, a moment when all matter and energy were compressed into an infinitely small, dense point. Yet this origin story invites more questions than answers. What sparked this initial expansion? What preceded the Big Bang? These remain profound mysteries at the frontier of cosmology. At the heart of Einstein's theory lies the revolutionary insight that space and time are not separate entities but are interwoven into a four-dimensional continuum known as space-time. This idea upends classical notions and introduces mind-bending phenomena such as time dilation, where time flows differently depending on the observer's speed or gravitational field, and the universal speed limit set by the speed of light, approximately 186,000 miles per second. This speed limit leads to another cornerstone of physics, the equivalence of mass and energy, encapsulated in the iconic equation E equals mc². This relationship underpins much of modern physics, from the reactions powering the stars to the intricacies of particle physics. General relativity further redefines gravity not as a force, but as the curvature of spacetime caused by mass and energy. Massive bodies like stars and planets warp the spacetime around them, guiding the paths of other objects, much like a marble rolling on a warped rubber sheet. This perspective allows us to understand remarkable phenomena such as gravitational lensing, where light bends around massive objects, enabling astronomers to observe galaxies hidden behind cosmic obstacles. It also explains how black holes trap everything within their event horizons by bending spacetime to an unimaginable degree. The theory of relativity also informs our comprehension of the universe's evolution, helping scientists map its past, present, and future. It predicts and explains the cosmic microwave background radiation, a faint glow left over from the early universe, and underlies models of cosmic expansion, dark energy, and the large-scale structure of the cosmos. One of the most tantalizing and speculative predictions arising from general relativity is the existence of wormholes, or Einstein-Rosen bridges. Imagine folding a sheet of paper and piercing a hole through it so that two distant points connect instantly. This analogy captures the essence of a wormhole, a theoretical shortcut through space-time that could link far-flung regions of the universe. If stable and traversable, wormholes might allow for faster-than-light travel without violating the cosmic speed limit. Yet wormholes introduce deep puzzles. Their stability likely requires exotic matter with negative energy density, a form of matter yet to be observed. Quantum effects might cause wormholes to collapse too quickly to be useful as cosmic tunnels. Moreover, wormholes raise paradoxes involving causality and time travel. Could they permit journeys into the past, triggering paradoxes like the infamous grandfather paradox? Physicists explore whether fundamental laws prevent such paradoxes, or if self-consistency principles ensure time travel actions are part of a coherent timeline. If wormholes do exist, they could transform our understanding of the universe's topology. They might connect not only distant points within our universe, but also entirely separate universes, opening gateways to a multiverse, a concept both thrilling and deeply mysterious. Through the lens of relativity, reality becomes a dynamic, interconnected tapestry, challenging our perceptions and beckoning us toward deeper truths about the cosmos and our place within it. This theory does not merely explain gravity, it transforms it into a profound exploration of space, time, and the infinite possibilities woven into the universe's fabric. This raises profound questions about the very fabric of reality, the intricate structure of the cosmos, and the tantalizing possibility that our universe may be but one of countless others nestled within a vast multiverse. Wormholes, enigmatic tunnels through space-time, remain shrouded in mystery. They invite us to question the nature of exotic matter, the boundaries of causality, and the foundational principles that govern existence itself. As gateways to the unknown, wormholes stand as one of the most thrilling and perplexing concepts in modern theoretical physics. And then there is the multiverse theory, a bold proposition that suggests an infinite tapestry of universes beyond the one we call home. These parallel worlds, sometimes called alternate realities, could exist in different dimensions or frequencies, each governed by its own unique physical laws, constants, and even distinct forms of life. This mind-bending idea draws strength from various scientific frameworks, including cosmic inflation, quantum mechanics, and string theory. The seeds of the multiverse concept were planted in the moments just after the Big Bang, during an explosive era known as cosmic inflation. Physicist Alan Guth proposed that our universe is merely one bubble among an endless froth of universes, each forming independently with its own cosmic blueprint. Quantum mechanics deepens this mystery with the many worlds interpretation, suggesting every quantum event branches into a new universe, creating a boundless web of parallel realities. Meanwhile, string theory, with its complex mathematical dance, hints at hidden dimensions and universes beyond human perception. Yet, for all its allure, the multiverse remains elusive, perched just beyond the reach of empirical proof. Unlike established scientific theories grounded in observable data, the multiverse hypothesis dwells in a realm of speculation. If these universes exist, each one is likely isolated, locked away from direct observation, making the pursuit of concrete evidence a staggering challenge. This uncertainty fuels ongoing debate. Is the multiverse a scientific theory, a philosophical musing, or something in between? Philosophically, the implications are staggering. If infinite universes exist, what does that say about the uniqueness of our own? Why do the physical constants in our universe appear so finely tuned to allow life? This question leads to the anthropic principle, the idea that we observe a life-friendly universe simply because only such a universe can support observers like us. Some dismiss this as a circular argument, leaving many unsatisfied but intrigued. Moreover, questions linger about the interaction or isolation of these universes. Could there be leaks or crossings between them, or are they forever sealed off from one another? These puzzles push the boundaries of our understanding of space-time and existence itself. In the end, the multiverse theory stretches our intellectual horizons, inspiring awe and curiosity as much as it challenges certainty. It invites scientists and philosophers to venture into uncharted realms of thought, where the mysteries of reality unfold in endless, shimmering possibilities. And so begins a journey into the heart of modern physics, where bold ideas reshape our understanding of the cosmos. M-theory and string theory offer revolutionary frameworks that challenge centuries-old notions about the universe's fundamental nature. Unlike traditional physics, which treats particles as tiny points, these theories propose that the universe is woven from one-dimensional strings, vibrating threads whose different modes of oscillation give birth to the diverse particles that compose everything we know. Imagine an electron as a string vibrating in one way, while a quark dances to a different rhythm. This elegant concept unites all particles and forces under a single breathtaking umbrella, aiming to deliver the long-sought theory of everything, a framework that could finally reconcile the baffling gap between quantum mechanics and general relativity. Yet, the story grows even stranger. String theory predicts the existence of extra dimensions beyond our familiar 3 of space and 1 of time. The most studied variant, known as Type 2a string theory, demands a total of 10 dimensions to work mathematically. But where are these hidden realms? The answer lies in the notion of compactification. These extra dimensions are curled up so tightly in intricate shapes smaller than anything we can detect that they evade direct observation. Intriguingly, the precise form of these curled-up dimensions can shape the particles and forces that emerge in our perceivable 4-dimensional universe. This might explain the delicate fine-tuning of physical constants that make life possible, a cosmic puzzle that has puzzled scientists for decades. But the narrative does not end here. M-theory steps forward as an ambitious extension, uniting 5 distinct string theories into a single, coherent framework and proposing an 11th dimension. In this vision, our entire universe could be a 3-dimensional brain floating within a higher dimensional space, perhaps alongside countless other brains. This radical brain-world perspective could explain one of physics' greatest mysteries: why gravity is so much weaker than the other fundamental forces. If gravity spreads through these extra dimensions, while forces like electromagnetism remain trapped on our 3-dimensional brain, its relative feebleness becomes a natural consequence of geometry. At the frontier of these theories lies the enigmatic black hole. regions where gravity crushes matter into seemingly infinite density, and our current laws of physics falter. String theory provides groundbreaking insights into black holes' inner workings, at explaining their entropy and temperature in ways that complement Stephen Hawking's revolutionary discovery of black hole radiation. These advances hint that the troubling singularities predicted by general relativity might be smoothed over by the principles of strings and brains, promising a deeper, more complete understanding of the universe's fabric. Despite these extraordinary prospects, profound challenges remain. The energies required to test string theory's predictions lie far beyond the reach of today's most powerful particle accelerators. Moreover, the vast landscape of possible solutions, endless configurations of extra dimensions and strings, makes pinpointing the exact version describing our universe a monumental task, demanding novel mathematics and ingenious experiments. Meanwhile, although M-theory offers a tantalizing blueprint for unification, it remains a work in progress, with many pieces of the puzzle yet to be discovered. In the end, string theory and M-theory stand as bold beacons in the quest to unravel the cosmos, transforming our understanding of particles, forces, and dimensions. They promise answers to some of physics' deepest mysteries, while sparking new questions that drive the ceaseless human pursuit of knowledge, inviting us to peer ever deeper into the grand tapestry of existence. And the Great Attractor stands as one of the most baffling and captivating mysteries in modern astrophysics. Nestled roughly between 150 and 250 million light-years away, in the celestial region framed by the Centaurus and Hydra constellations, this enormous gravitational anomaly exerts a powerful pull on countless galaxies, including our own Milky Way and its neighbor, the Andromeda Galaxy. It is not just a force, it is a cosmic conductor orchestrating a vast, collective motion known as the bulk flow, an immense tide of galaxies all moving together through the fabric of space toward this unseen gravitational beacon. Yet, what deepens the enigma of the Great Attractor is its hidden nature. It resides in what astronomers call the zone of avoidance, a swath of the sky cloaked behind the dense galactic plane of the Milky Way. This plane is a dense veil of stars, dust, and gas that obscures optical telescopes, rendering direct observation nearly impossible. Even with the advent of advanced technologies like X-ray astronomy and radio wave surveys, astronomers find their view blocked and their clues fragmentary. What lies behind this cosmic curtain remains largely speculative, as the Great Attractor's true form is concealed in shadows. Scientists theorize that this gravitational powerhouse could be a colossal supercluster of galaxies, an immense concentration of mass so dense it warps the paths of surrounding galaxies. Some even speculate the presence of unseen dark matter, a mysterious, invisible substance making up about 85% of the universe's mass, pulling the cosmic strings from behind the scenes. The gravitational forces traced back to the Great Attractor hint at a cosmic hierarchy, where even larger structures like the Shapley supercluster may be entwined in this cosmic dance, influencing the flow of galaxies on scales unimaginable. This multi-layered gravitational network reveals a universe far more intricate than once thought, a tapestry woven from giant cosmic attractors whose interactions shape the grand architecture of the cosmos. Unlocking the secrets of the Great Attractor offers more than understanding a single anomaly. It may provide vital insights into the elusive nature of dark matter and its pivotal role in the evolution of galaxies and the universe itself. As astronomers push the boundaries of observation, probing with ever more sensitive instruments, the Great Attractor remains a tantalizing puzzle. Its gravitational pull is a silent whisper from the depths of the universe, beckoning researchers to uncover the hidden structures of the cosmos and the unseen forces at play. The quest to reveal this cosmic mystery fuels one of the most exciting frontiers in astrophysics today, a journey toward comprehending the universe's unseen scaffolding and the fundamental forces shaping our cosmic neighborhood. Typically lasting only a few milliseconds, these bursts unleash in that fleeting moment more energy than the sun radiates in an entire day. Since their groundbreaking discovery in 2007, over 1,000 fast radio bursts, or FRBs, have been detected, yet their true origins and the mechanisms behind them remain shrouded in mystery. One of the most compelling enigmas surrounding FRBs is their source. While some appear as singular, isolated events, others have been observed to repeat, originating consistently from the same region of space. This fascinating distinction hints at a diverse range of astrophysical phenomena driving these bursts, each posing unique scientific challenges. Non-repeating FRBs may stem from catastrophic cosmic occurrences, such as the explosive death throes of massive stars in supernova or the violent mergers of neutron stars. These dramatic events unleash a single, powerful burst of energy before fading into silence. Conversely, the repeating FRBs suggest a more persistent and stable astrophysical engine. Among the prime suspects are magnetars, neutron stars endowed with unimaginably strong magnetic fields, capable of unleashing bursts of high-energy radiation through mechanisms still under intense investigation. Equally puzzling is the distribution of FRBs across the cosmos. They appear scattered randomly across the sky without any obvious pattern or clustering, suggesting origins from distant galaxies scattered throughout the universe. The sheer scale of energy required for these bursts to be detected across such vast distances adds to the mystery. As these radio waves traverse the cosmos, they interact with intergalactic matter, which can distort their signals, but also provide crucial clues about the environments they pass through. By studying the way the bursts disperse, where different frequencies arrive at Earth at staggered intervals, scientists can estimate how far they have traveled, yet pinpointing their precise origin remains a formidable challenge. Further complicating the puzzle are some of the unusual characteristics observed in certain FRBs, including variations in polarization and fluctuations in brightness. Extreme changes in polarization imply that the signals have passed through intensely magnetized regions, possibly near supermassive black holes or within the environments of magnetars. The broad diversity in FRB properties, spanning frequency ranges, durations, and intensities, strongly suggests that multiple origins and physical processes are at play, making it difficult to fit all observations into a single theoretical model. The stakes of unraveling the mysteries of FRBs are high. If these phenomena can be systematically observed and accurately traced, they could serve as powerful cosmic probes, illuminating the distribution of matter throughout the universe and deepening our understanding of its large-scale structure and evolution. Some speculative theories even entertain the possibility that certain FRBs might be signals sent by advanced extraterrestrial civilizations, though this idea remains controversial and unproven. Amid this cosmic intrigue, the WOW signal stands out as one of the most famous and enigmatic detections in the quest to find extraterrestrial intelligence. On August 15, 1977, astronomer Jerry R. Ehman recorded an intense, narrowband radio signal while working on the SETI project at Ohio State University's Big Ear Radio Telescope, lasting just 72 seconds. The maximum duration the telescope could track the source before Earth's rotation shifted its view. The signal was so extraordinary in strength and character that Ehman circled the data on the printout and wrote, "Wow, wow," in the margin, giving the signal its iconic name. What made the WOW signal so remarkable was not only its intensity, but also its frequency, approximately 1,420 megahertz, the natural emission line of hydrogen, the universe's most abundant element. This frequency has long been considered an ideal channel for interstellar communication, as hydrogen's ubiquity offers a universal language for any technologically advanced civilization seeking contact. The signal's narrow bandwidth and strength fueled hopes it might represent an artificial transmission rather than random cosmic noise or terrestrial interference. Despite countless follow-up observations, the WOW signal has never been detected again. Its exact source remains unidentified, fueling endless speculation, from Earth-based interference to a one-time cosmic event or an intentional extraterrestrial broadcast. The failure to observe or repeat has made it impossible to conclusively categorize the signal, keeping it a tantalizing mystery in the annals of SETI research. Various hypotheses have been explored, including reflections from space debris, yet none have satisfactorily explained the signal's unique properties. The WOW signal's enduring significance lies not only in what it might have been, but in how it galvanized a generation of scientists and enthusiasts in the search for cosmic company. It remains a powerful symbol of humanity's yearning to understand our place in the universe, inspiring ongoing efforts to listen deeper, look farther, and ask the ultimate question: are we alone? And so, it stands as a defining milestone, showcasing humanity's incredible ability to detect potential extraterrestrial signals. This achievement not only ignites curiosity but fuels a relentless drive for scientific discovery. It highlights the critical importance of persistent, diverse monitoring of the skies, employing a vast array of technologies and methods designed to capture elusive, fleeting signals that might otherwise slip through unnoticed. Among these enigmatic detections, the WOW signal remains one of the most compelling enigmas, a tantalizing beacon in the search for extraterrestrial intelligence. It encapsulates both the immense promise and daunting challenges of this cosmic quest. This signal calls us to keep our minds open and our tools ever advancing, fostering the enduring hope that one day we might unravel this cosmic mystery. But the mysteries of space don't end there. The Pioneer anomaly tells a story of unexpected intrigue far beyond Earth. This phenomenon refers to the puzzling deviations in the flight paths of the Pioneer 10 and Pioneer 11 spacecraft after they journeyed past Saturn's orbit. Launched by NASA in the early 1970s, these spacecraft were trailblazers, venturing deeper into the outer solar system than ever before, equipped with instruments to study the distant planets. Yet, during their long missions, scientists noticed something strange. Both crafts were experiencing a subtle, persistent acceleration towards the sun, a slowdown not predicted by the known laws of physics or gravitational forces from other celestial bodies. This slight anomaly, about 8.74 times 10 meters per second squared, persisted over vast distances in time, presenting a profound puzzle. Precise tracking data brought this mystery to light, challenging experts to identify its cause. Early hypotheses spanned from expected influences like solar radiation pressure and heat emitted by the spacecraft's power systems to more speculative theories invoking the need for new physics, perhaps even questioning Newtonian gravity or proposing the involvement of dark matter. Despite exhaustive analyses, the anomaly remained unresolved for years, spawning an array of scientific debates. One of the more grounded explanations focused on the spacecraft themselves. Heat emitted by their onboard systems, including radioactive power sources, could create a gentle recoil effect. This thermal recoil force arises from heat being radiated unevenly in certain directions due to the spacecraft's design, subtly nudging their paths off course. However, accurately modeling these emissions to fully explain the anomaly was an enormous challenge. Meanwhile, more radical ideas suggested this anomaly could hint at revolutionary physics, signaling a gap in our understanding of gravity or unknown forces lurking in interstellar space. Such proposals fueled spirited debates because confirming them would require new observations far beyond the capabilities of the Pioneer missions alone. In recent years, advancements in thermal modeling and detailed spacecraft data analyses have increasingly supported the thermal recoil hypothesis, suggesting that these heat emissions do, in fact, account for much of the anomaly. Yet, despite this progress, the Pioneer anomaly retains a sense of wonder and continues to inspire curiosity. It stands as a humbling reminder of how much we still have to learn and the vital role of precision, innovation, and perseverance in scientific exploration. This anomaly is more than a footnote in space exploration. It is a powerful case study illuminating the intricate challenges of navigating the cosmos over decades. Whether the mystery is fully resolved by conventional physics or points toward new realms of knowledge, the Pioneer anomaly underscores the need for vigilant observation and an open mind in our pursuit of understanding the universe. Then there is the Kuiper Cliff, a dramatic and unexpected drop-off in the number of objects beyond a certain distance within the Kuiper Belt. This distant region, stretching roughly 30 to 55 astronomical units from the Sun, mirrors the asteroid belt but on a far grander scale. It is a vast repository of ancient remnants from the solar system's formation, including dwarf planets like Pluto and innumerable icy bodies. The sudden decline, known as the Kuiper Cliff, challenges astronomers to rethink the dynamics and history of this mysterious frontier, reminding us that even in our cosmic backyard, surprises await those who dare to look deeper. And so, astronomers set out with clear expectations. As objects in our solar system moved farther from the Sun, their numbers should slowly dwindle. Yet what they actually discovered was something far more astonishing, a sudden, Steep drop-off in the population of these distant bodies beyond roughly 50 astronomical units, a boundary now known as the Kuiper Cliff. This mysterious edge defies the neat predictions of classical models of solar system formation and poses a profound puzzle about the forces and events that sculpted our cosmic neighborhood. The Kuiper Cliff isn't just a curiosity, it challenges our understanding of how the solar system took shape. One gripping theory suggests the gravitational grip of an unseen giant, an elusive Planet 9. This hypothetical world, perhaps several times the mass of Earth and lurking far beyond Neptune, might be the celestial architect behind this cosmic clearing, its gravity sweeping away or scattering smaller Kuiper Belt objects. But despite rigorous searches with some of the most powerful telescopes on Earth, this giant remains a phantom, its existence tantalizing but unproven. Alternatively, this enigma may reveal cracks in our very models of planetary genesis. The early solar system was a chaotic arena, with swirling gas and dust giving birth to planets, while giant bodies like Jupiter and Saturn migrated, their massive gravitational forces stirring the cosmic pot. Perhaps the Kuiper Cliff is the fingerprint of complex interactions, stellar flybys in the sun's youth, or gravitational nudges from these massive planets that our current simulations have yet to fully capture. The implications stretch even further. What lies beyond the Kuiper Cliff? Could other pockets or gaps exist farther out, whispering secrets of our solar system's tumultuous past? To unlock these mysteries, astronomers call for deeper, more sensitive observations, telescopes tuned to spot the faintest, most distant objects in the dark reaches beyond Neptune. Each new discovery could reshape our cosmic map, revealing hidden dynamics and the true architecture of the outer solar system. Meanwhile, another frontier of cosmic exploration was revolutionized by the discovery of gravitational waves, ripples in the very fabric of space-time, predicted a century earlier by Albert Einstein's general relativity. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, captured these elusive waves for the first time, opening a new window onto the universe's most violent phenomena. These waves emanate from cataclysms like colliding black holes and merging neutron stars, cosmic dances that twist and ripple space-time itself. Gravitational wave astronomy has transformed our understanding of these enigmatic objects. It has unveiled black holes of unexpected mass and spin, forcing a rethink of stellar evolution theories. The fusion of neutron stars observed through both gravitational waves and traditional electromagnetic signals has illuminated the origins of some of the universe's heaviest elements, gold and platinum, born in these cosmic crucibles. Moreover, these waves provide an unparalleled laboratory for testing Einstein's theory itself. By scrutinizing the precise patterns of these space-time ripples, scientists push the boundaries of general relativity by searching for cracks or surprises that might reveal new physics. So far, Einstein's masterpiece remains unbroken, but future detections could yet rewrite the laws of gravity as we know them. Together, the Kuiper Cliff and gravitational waves represent two profound frontiers in modern astronomy, one probing the hidden architecture of our solar system, the other unveiling the deepest mysteries of the cosmos. Both remind us how much remains to be discovered in the vast expanse around us, where mysteries beckon just beyond the edge of our knowledge. Moreover, there lies the tantalizing possibility of detecting gravitational waves originating from the dawn of time itself, the earliest moments after the Big Bang. These primordial ripples in the fabric of space-time offer a direct window into conditions that existed when the universe was less than a fraction of a second old. Unlike traditional electromagnetic observations, which show us only light and radiation emitted long after these events, primordial gravitational waves could reveal the universe's rapid inflationary phase, a mysterious burst of expansion that shaped everything we see today. Unlocking these signals would provide profound insights into the fundamental nature and origins of the cosmos, pushing the boundaries of our knowledge further than ever before. Despite the groundbreaking advances in gravitational wave detection, many cosmic mysteries remain. While scientists have identified the sources of many signals, colossal events like merging black holes and neutron stars, some waves still arrive without a clear origin. These enigmatic signals may come from exotic phenomena such as boson stars, cosmic strings, or other yet undiscovered entities lurking in the cosmic shadows. As our detection instruments grow ever more sensitive, with facilities like LIGO in the United States and Virgo in Europe leading the charge, and future missions such as the space-based LISA Observatory on the horizon, the promise of unveiling these unknown sources becomes increasingly real. Gravitational waves have not only confirmed a key prediction of Einstein's theory of general relativity, but have also inaugurated a new era in astronomy, one where we do not just observe the universe through light, but listen to its deepest cosmic symphonies. These waves allow us to perceive events so violent and extreme they were once hidden from view. The collision of black holes, the merging of neutron stars, and potentially the echoes of the universe's birth itself. Each detection provides answers to long-standing questions, but also sparks new mysteries, setting the stage for decades of scientific exploration. Imagine a pebble dropped into a still pond, sending ripples spreading outward. Gravitational waves are just such ripples, but instead of water, they travel through the very fabric of space-time. Detecting these waves demands instruments of extraordinary precision. LIGO and Virgo, with their immense L-shaped arms stretching over 2 miles, can measure distortions smaller than 1,000th the diameter of a proton as gravitational waves pass through Earth. This level of sensitivity is a testament to human ingenuity and the power of modern technology to unlock the universe's secrets. Yet, even with these monumental achievements, the story is far from complete. Gravitational waves span a vast spectrum, much of which remains unexplored. Waves from the Big Bang itself could carry encoded messages from the universe's infancy, while others might hold clues to the nature of dark matter, the invisible substance comprising about 85% of all mass in the cosmos, yet still shrouded in mystery. As detection methods evolve, gravitational wave astronomy promises to transform our understanding of physics, potentially revealing new forces, particles, or dimensions, and reshaping our grasp of space, time, and gravity itself. Alongside these cosmic phenomena lies the equally puzzling world of quantum entanglement, a cornerstone of quantum mechanics that challenges our classical intuition. When two particles become entangled, their quantum states become so deeply intertwined that the state of one instantly influences the other, no matter the distance separating them, even if they are light years apart. This phenomenon, famously dubbed spooky action at a distance by Albert Einstein, seems to defy the cosmic speed limit set by relativity, where no information should travel faster than the speed of light. Experimental evidence for entanglement is overwhelming. Consider entangled photons. If one photon's polarization is measured and known, the other's polarization becomes immediately certain regardless of the space between them. This interconnectedness hints at a profound underlying unity in the universe, a web of relationships that transcends ordinary space and time. The mystery of quantum entanglement goes beyond mere curiosity. It sparks foundational questions about reality itself and has practical implications that could revolutionize technology. Quantum computing, which exploits entanglement to perform computations far beyond the reach of classical computers, and quantum encryption, promising unprecedented security, both arise from this enigmatic quantum link. Though quantum mechanics mathematically describes entanglement perfectly, the true nature of how and why these instantaneous connections occur remains an open question, a profound puzzle that continues to drive physicists into uncharted intellectual territory. Together, gravitational waves and quantum entanglement illuminate the vast complexity of the universe, from its cosmic birth to the subatomic dance of particles. They beckon us to listen more closely, look deeper, and rethink the very foundations of reality, promising a future rich with discovery and wonder. And the realm of cosmology unfolds as a vast, mesmerizing frontier, an immense tapestry woven with profound mysteries that continue to challenge and captivate the brightest minds in science. Among these enigmas, none loom larger than the elusive nature of dark matter and dark energy. Dark matter, constituting roughly 27% of the universe's total mass energy content, exerts a silent but powerful gravitational pull, shaping galaxies and cosmic structures, yet it remains invisible, undetectable by any form of light or electromagnetic radiation. Even more mystifying is dark energy, an invisible force making up about 68% of the cosmos, responsible for driving the universe's accelerated expansion, a phenomenon that has upended traditional cosmological models. Yet, what exactly are these shadowy components? Are they unknown particles lurking beyond the reach of current detectors, or do they hint at a radical revision of the very laws of gravity that have guided physics for centuries? This question cuts to the heart of modern cosmology, pushing scientists to innovate new technologies, develop novel theories, and rethink the foundations of physics itself. And while we peer into the darkness, another profound mystery beckons: the origin and ultimate fate of the universe. The Big Bang Theory, our best model so far, describes the universe's explosive birth from an unimaginably hot, dense state. But what sparked this cataclysmic event? What, if anything, preceded it? These questions remain stubbornly unanswered, veiled behind a cosmic curtain of uncertainty. Looking ahead, the universe's destiny hangs in the balance. Will it expand forever into a cold, empty abyss? Will it collapse back into a fiery implosion known as the Big Crunch? Or will it tear itself apart in a cosmic apocalypse dubbed the Big Rip? The answers depend intimately on the true nature of dark energy and the universe's geometry, both still shrouded in mystery. Moreover, the universe reveals yet another perplexing asymmetry: the overwhelming dominance of matter over antimatter. The laws of physics predict equal amounts of both should have emerged, annihilating each other and leaving behind a barren void. Instead, a tiny imbalance favored matter, allowing stars, planets, and life itself to exist. Understanding why this cosmic preference occurred is one of the grandest puzzles of all, with profound implications for our very existence. But the universe's mysteries do not stop there. Cosmic voids, enormous regions spanning millions of light years, are vast expanses nearly empty of galaxies, stars, and ordinary matter. These immense voids pose a paradox. How can such emptiness exist in a universe so rich with matter? Traditional cosmological models anchored in gravity's pull causing matter to clump and form structures are challenged by these yawning gaps. While not completely barren, they harbor sparse hydrogen gas and dark matter. Their origin, growth, and influence remain active fields of research. Cosmic voids offer a unique laboratory, allowing scientists to test cosmological theories, especially the lambda cold dark matter, LCDM model, which attempts to describe the universe's evolution through the interplay of dark matter and dark energy. In the shadows of these voids, subtle deviations between theoretical predictions and observations could unveil new physics, hinting that our current understanding, successful though it is, might be incomplete. Each discovery pushes us closer to unraveling the true fabric of the cosmos and its grand destiny. Meanwhile, streaking through space at nearly the speed of light, high-energy cosmic rays bombard Earth's atmosphere, igniting spectacular cascades of secondary particles detectable by ground-based observatories. These subatomic messengers, often protons or atomic nuclei, originate from violent cosmic events, but their precise sources remain shrouded in mystery. While lower-energy cosmic rays linked to solar flares or supernova remnants, their ultra-high energy counterparts, surpassing 10 to the 19 electron volts, defy easy explanation. Possible origins range from the hearts of active galactic nuclei to gamma-ray bursts, or even exotic relics from the early universe, particles born from primordial chaos. And how do these cosmic bullets traverse the vast interstellar expanse, maintaining their extraordinary energies despite magnetic fields that twist and scatter their paths? Tracing their origins remains one of astrophysics' most daunting quests, promising insights not only into cosmic accelerators, but also into the fundamental nature of space itself. In this grand documentary of the cosmos, every question answered reveals deeper mysteries, each discovery a stepping stone toward a more profound understanding of the universe, our place within it, and the unseen forces shaping all that exists. Additionally, their interactions with the cosmic microwave background radiation lead to subtle but significant energy losses, adding layers of complexity to our understanding of how these particles propagate and distribute across the cosmos. This phenomenon, known as the GZK cutoff, named after Greisen, Zatsepin, and Kuzmin, suggests a theoretical upper limit to the energy cosmic rays can retain after traversing the immense distances of the universe. By probing these high-energy cosmic rays, scientists aim to unlock profound insights into their mysterious origins and the fundamental mechanisms governing high-energy particle physics. This pursuit holds the promise of revealing new phenomena and forces that sculpt the universe on its grandest scales. The depths of space remain a vast frontier teeming with unknowns, where our current instruments and theories offer only fleeting glimpses of what might lie beyond. One of the most captivating possibilities involves exotic cosmic objects such as primordial black holes. Unlike the black holes formed from the collapse of massive stars, these primordial black holes could have emerged in the chaotic moments just after the Big Bang, born from dense fluctuations in the fabric of the early universe. Their sizes could range dramatically, from minuscule subatomic scales to giants weighing thousands of times the mass of our sun. Detecting these elusive entities could unlock critical clues about dark matter, the invisible substance that makes up much of the universe's mass but remains profoundly mysterious. Beyond black holes, theoretical constructs like wormholes stir the imagination. Predicted by solutions to Einstein's field equations, wormholes are envisioned as tunnels or shortcuts through the very fabric of space-time. If they exist, wormholes could link distant regions of space and time, potentially enabling faster-than-light travel and opening new horizons for cosmic exploration. However, questions about their stability and the possibility of traversing such structures remain firmly in the realm of theory, with no experimental evidence yet to confirm their reality. Equally intriguing is the concept of parallel universes or a multiverse. This radical idea suggests our universe may be just one among many, each governed by distinct physical laws and constants. Emerging from interpretations of quantum mechanics and string theory, the multiverse hypothesis paints a picture of reality far richer and more complex than previously imagined, hinting at infinite diversity beyond our observable cosmos. Moreover, the universe might harbor unknown forms of energy and matter, entities unlike any particles or forces currently cataloged by science. These could include new varieties of neutrinos, elusive particles predicted by extensions to the standard model of particle physics, or entirely novel states of matter. The discovery of such phenomena could revolutionize our understanding of the cosmos, offering solutions to long-standing mysteries such as the nature of dark energy, the enigmatic force driving the universe's accelerating expansion, and the finely tuned physical constants that allow life to flourish. In this unfolding cosmic saga, each breakthrough brings us closer to deciphering the profound secrets hidden within the vastness of space, revealing a universe far stranger and more wondrous than we ever imagined.